Please subscribe to support the channel. We're about to take a journey across the cosmos, not to any ordinary star, but to a true giant that dominates the night sky in its own quiet, subtle way. This is not one of the dazzling beacons like Sirius or Betelgeuse that instantly draw the eye, but instead a star that hides its immensity behind faint light. Its name is R Doradus, and though it may not blaze as one of the brightest stars overhead, it holds the distinction of being the largest star visible to the naked eye from Earth. That's right, when we look up at the southern skies and spot R Doradus, we are gazing upon the single largest stellar body we humans can actually see without the help of a telescope. The thought itself is thrilling. Somewhere out there in the dark depths of space, a colossal red giant, hundreds of times wider than our Sun, shines faintly enough that most people would never guess the extraordinary scale they're witnessing. What makes this fascinating is that when most of us think of stars, we think of twinkling points of light that look more or less the same. But R Doradus is a reminder that appearances in the sky can be deceiving. Its relatively modest brightness disguises its status as a true leviathan, a giant among giants. To put it into perspective, you could line up hundreds of suns across its diameter, and yet from our vantage point, it seems nothing more than a dim star. That contradiction, something so big, appearing so small, is part of the mystery and wonder of astronomy. This is the journey we are about to embark on, uncovering the secrets of R Doradus. Over the course of this deep exploration, we'll step through its enormous scale, its cosmic neighborhood, its life as a star nearing the twilight of its stellar evolution, and its eventual fate. We'll compare it to other stars like Betelgeuse and UY Scuti, place it within the grand puzzle of stellar life cycles, and reflect on how such objects shape not only the galaxy but the very building blocks of life itself. Each step will peel back another layer of this understated yet colossal star, making us appreciate just how astonishing the universe can be. R Doradus is more than just a star, it's a story written in light, a cosmic drama unfolding over millions of years, and a living laboratory for astronomers trying to understand how stars grow old and die. By the end of this journey, you'll never look at the faint stars of the night sky the same way again, because hidden among them could be giants, immense, fiery worlds that defy our imagination. And among them, R Doradus stands out as one of the most fascinating. When we talk about stars, it's easy to imagine that they're all basically the same, glowing orbs scattered across the black canvas of the universe, shining like identical pinpricks of light. But in reality, the stellar family is an incredibly diverse one, with members ranging from tiny, dense remnants barely larger than a city, to gargantuan, bloated supergiants that could engulf entire planetary systems. To truly appreciate what makes R Doradus so unique, we first need to set the stage by understanding this grand spectrum of stellar sizes. Only then can we see where this quiet but colossal star fits into the cosmic hierarchy. At the smallest end of the stellar scale, we find the white dwarfs. These are the remains of stars like our Sun after they have exhausted their fuel and shed their outer layers. A white dwarf is roughly the size of Earth. Yes, imagine compressing something as massive as the Sun into a ball no bigger than our planet. Their density is almost beyond comprehension. A single teaspoon of white dwarf material would weigh several tons. White dwarfs don't burn fuel anymore. Instead, they shine faintly with residual heat, slowly cooling over billions of years. They're the ghosts of stars, remnants that silently mark the passage of stellar time. Moving up from white dwarfs, we encounter the red dwarfs, which are the most common type of star in our galaxy. Despite their abundance, they're so small and dim that not a single one is visible to the naked eye from Earth. These stars are far smaller than the Sun, often just a fraction of its size and mass, but they burn their fuel at a much slower rate. That means they live unimaginably long lives. Some red dwarfs may last for trillions of years, far outliving the current age of the universe itself. In cosmic terms, they are the quiet, steady workers of the galaxy, holding galaxies together with their sheer numbers. Then there are stars like our Sun, which is classified as a G-type main sequence star. In the middle range of size and brightness, the Sun is by no means extraordinary in cosmic terms, but to us, it's everything. Its balance of mass and luminosity provides a habitable environment for Earth. Stars like the Sun fuse hydrogen into helium in their cores for billions of years, sustaining themselves with a delicate balance between the outward pressure of fusion and the inward pull of gravity. But even the Sun, which feels immense to us, is modest compared to the giants waiting further up the scale. Next come the giants, stars that have left the stable main sequence phase and have expanded enormously. When a star like the Sun exhausts the hydrogen in its core, it begins fusing helium and other elements, causing it to swell into a red giant. At this stage, its diameter can balloon hundreds of times beyond what it once was. If the Sun were to become a red giant today, its swollen outer layers would likely engulf Mercury and Venus, and possibly even Earth. Giants remind us that stars are not static, but living entities that grow, evolve, and transform dramatically over their lifetimes. And then, towering over even these giants, we find the supergiants and hypergiants. These are the monsters of the stellar kingdom, stars so massive that they live fast and die young. Betelgeuse, for example, is a red supergiant located in Orion, and it dwarfs our Sun to a shocking degree. Its radius is thought to be more than 750 times larger than the Sun's. But Betelgeuse isn't even the largest known. Stars like UY Scuti and VY Canis Majoris push the limits of stellar size, swelling to radii over 1,000 times that of the Sun. If UY Scuti were placed at the center of our solar system, its outer surface would stretch beyond the orbit of Jupiter. These supergiants are rare, unstable, and destined to end in cataclysmic supernovae, scattering their enriched guts across the galaxy. This wide variety demonstrates that stars are not uniform points of light, but complex, evolving entities that occupy a staggering range of scales. From tiny Earth-sized remnants to titanic orbs that could contain thousands of suns, the diversity of stars shapes the tapestry of the universe itself. It also reminds us that appearances can be misleading. A faint star in the night sky may actually be colossal in size but far away or dim in visible light, while a bright star might be relatively small but close to Earth. Now, against this grand background of stellar diversity, R Doradus stands out as a particularly fascinating member of the family. It is not the most massive, nor the brightest, nor the most famous. But it holds a distinction that immediately makes it special. It is the largest star that can be seen with the naked eye. Even though it doesn't dazzle us like Sirius or shine crimson like Betelgeuse, R Doradus is quietly humbling in its sheer physical scale. Understanding just how it fits into the cosmic scale of stars helps us prepare for the deeper exploration of what makes it unique. It's important to keep this range of stellar sizes in mind as we continue, because much of what makes R Doradus so impressive is how it pushes the boundaries of what's visible to human eyes. If you lined up the entire spectrum, from tiny white dwarfs to galaxy-defining hypergiants, R Doradus would sit firmly in the upper echelon, not the very top, but high enough to remind us just how astonishingly large stars can become. Now that we've set the stage with the incredible range of stellar sizes, it's time to place R Doradus within this cosmic scale and understand what makes it so noteworthy. The galaxy is absolutely filled with massive stars, some dwarfing R Doradus in sheer diameter, others burning brighter and hotter than our Sun could ever dream of. Yet, despite the existence of far larger giants in the Milky Way, R Doradus holds the remarkable title of being the largest star that we, as human beings, can see with the unaided eye. That distinction alone makes it a treasure of the night sky, even if most people have never heard its name. Let's unpack that a little. Astronomers have catalogued stars that are truly beyond comprehension in size. Take UY Scuti, for example, often cited as one of the largest stars ever discovered. Its diameter is estimated to be more than 1,700 times that of the Sun. Another, VY Canis Majoris, is similarly immense, stretching so far across that it could easily engulf the orbits of the inner planets if placed where our Sun is now. These titanic stars utterly outclass R Doradus when it comes to raw volume and size. However, none of them can be seen with the naked eye. They are simply too far away and too faint in visible light for us to detect without telescopes. And this is where R Doradus becomes special. While it may not be the record holder for stellar gigantism, it bridges the gap between colossal scale and human perception. It is close enough to Earth and luminous enough that, under good conditions, you can actually spot it without any aid other than your own eyes. Think about how rare that is. The night sky is filled with stars that dazzle us, but most of the truly enormous ones hide behind the limits of visibility, tucked away in distant corners of the galaxy. R Doradus, in contrast, is not only huge but also near enough that we can directly perceive it as a faint point of light. This distinction underscores an important point about how we experience the universe. Astronomy is filled with objects of staggering scale, but our direct connection to them is often limited by distance. We cannot see most black holes, neutron stars, or hypergiants without sophisticated equipment. But R Doradus gives us a rare opportunity, an object that belongs to the elite class of stellar giants, yet one that ordinary human vision can still touch. It is, in a sense, the largest star accessible to the naked human eye. That makes it not just an astronomical fact but also a deeply human one. It's also worth noting that visibility doesn't always correlate with size. Many people know the star Betelgeuse, in the constellation Orion, because it glows brightly and distinctively red. Betelgeuse is indeed massive, much larger than R Doradus in terms of overall luminosity and visual impact. But here's the twist. R Doradus is technically larger in diameter than Betelgeuse, though far less bright. This comparison highlights just how counterintuitive the night sky can be. Brightness is not always a reflection of size. It's a combination of intrinsic luminosity, distance, and the type of radiation emitted. In galactic terms, R Doradus is not extraordinary. It doesn't rank among the absolute largest, and its mass isn't record-breaking. But from the perspective of human observation, it achieves something that none of the more distant giants can. It lets us see a stellar titan directly with our own eyes. That accessibility transforms it into a crucial astronomical subject. It's not just another red giant in the catalogue. It's a nearby laboratory for understanding how such stars live and die, how they interact with their surroundings, and how their vast atmospheres contribute to the enrichment of the interstellar medium. Imagine, for a moment, standing under the clear, dark skies of the southern hemisphere, gazing up at the constellation Dorado. Most people would never suspect that the faint that they see there is, in fact, the largest naked eye star in the heavens. That's the beauty of R Doradus. It's a hidden giant, modest in brightness but extraordinary in scale. When astronomers remind us that this inconspicuous speck is larger than nearly every other star we'll ever hear about, it changes the way we perceive that tiny point of light. In short, R Doradus is a cosmic paradox, a star that is both unassuming and extraordinary. Others may be larger, others may shine brighter, but none balance sheer size with naked eye visibility quite like this one. That's why placing it in context matters so much. It reminds us that even though astronomy deals with immense distances and objects far beyond ordinary experience, sometimes those wonders are close enough for us to witness directly, even if we don't immediately recognize their significance. When we talk about stars, part of their magic lies not just in their physical characteristics, but also in their place in the sky. For astronomers and casual stargazers alike, a star is never just a point of light. It's a landmark in the vast cosmic map overhead, tied to constellations and regions that help us navigate the universe. So, where exactly can we find R Doradus when we look up at the night sky? The answer lies in the constellation Dorado, a southern sky constellation that holds more than one astronomical treasure. Dorado is not one of the more famous constellations, at least not in the way Orion, Ursa Major, or Scorpius are widely recognized. Instead, it's a constellation that requires access to southern skies, and even then, it's not particularly striking in terms of brightness. Still, Dorado is astronomically rich. Its name means the dolphin fish in Spanish, and it was first introduced in the late 16th century by Dutch navigators exploring the southern seas. For those who live in the northern hemisphere, Dorado is a hidden part of the sky, forever below the horizon. But for observers in the southern hemisphere, it's a window into one of the most beautiful regions of the night sky. Why is Dorado so special? Because within its borders lies the Large Magellanic Cloud, LMC, one of the Milky Way's nearest galactic neighbors. The LMC is visible to the naked eye as a faint, misty patch of light, and it's brimming with clusters, nebulae, and massive star-forming regions. In fact, one of the most famous nebulae in the universe, the Tarantula Nebula, is located there. This makes Dorado a prized constellation for astronomers and astrophotographers. And tucked into this same celestial neighborhood, though much closer than the LMC, lies R Doradus, the giant we are focusing on. So how do you actually find R Doradus in the sky? The key is knowing that Dorado is best viewed from southern latitudes, especially between October and February, when it's high overhead in the evening skies. R Doradus itself doesn't stand out with dazzling brightness. Its magnitude usually hovers around 5th magnitude, sometimes dipping brighter or dimmer because it is a variable star. To the naked eye, that means it appears faint, just at the edge of visibility under good dark sky conditions. If you're in a city or somewhere with a lot of light pollution, spotting a Doradus may be nearly impossible. But under a dark, rural sky, it reveals itself as a faint star among the scattered points of Dorado. It's interesting to note how deceptive that faint point is. To the unaided eye, our Doradus looks utterly ordinary, blending in with the countless other faint stars of the southern sky. But when astronomers tell us that this dim speck is in fact the largest star the human eye can see, it completely changes the way we perceive it. Suddenly, Dorado is not just home to the large Magellanic Cloud, it's also home to a red giant of colossal proportions, hidden in plain sight. For context, Dorado is a constellation that lies relatively close to the south celestial pole, making it circumpolar for much of the southern hemisphere. That means for people living in places like Chile, Argentina, South Africa, or Australia, Dorado never truly sets. It just circles around the pole, always accessible at some point in the night. This makes a Doradus a star that southern observers can grow familiar with, provided they know where to look. Astronomers often use star charts and coordinates to pin down stars precisely. Our Doradus is located at right ascension 4 hours 36 minutes and declination -62 degrees 4 minutes, which places it firmly within Dorado's celestial boundaries. But for casual stargazers, it's easier to think of it like this. If you're in the southern hemisphere and you can find the large Magellanic Cloud, you're already close to the region where a Doradus resides. With a good star map or app, you can trace the constellation Dorado and identify the faint star that is, quite astonishingly, a red giant so large it dwarfs our solar system. This also highlights one of the bittersweet truths of stargazing. Many of the universe's most fascinating objects aren't the ones that shine most brightly in our skies. Instead, they can be subtle, tucked into constellations that don't grab attention at first glance. Our Doradus is a perfect example of this. It's easy to overlook, but once you know what it is, you'll never see Dorado the same way again. To summarize, the location of our Doradus is both specific and symbolic. Specifically, it lies in Dorado, a constellation best seen from southern latitudes, nestled in a region of sky famous for galactic wonders. Symbolically, it reminds us that cosmic greatness is not always obvious. Sometimes, the largest star visible to the naked eye appears as just another faint dot among billions, an unassuming point of light carrying a story far larger than anything we could imagine. When most people think of a star that is enormous in size, they naturally expect it to be one of the brightest jewels in the night sky. After all, if something is so vast that it dwarfs our sun many hundreds of times over, shouldn't it also blaze brilliantly across the heavens? And yet, when it comes to our Doradus, this expectation is misleading. Despite being the largest star visible to the naked eye, it is not among the brightest. In fact, it often goes unnoticed entirely unless you know exactly where to look. This contrast between brightness and size is one of the most intriguing aspects of stellar astronomy, because it reminds us that brightness is not a straightforward measure of a star's scale. Astronomers distinguish between two related but very different ideas: intrinsic luminosity and apparent brightness. Intrinsic luminosity is how much energy a star produces and radiates into space, essentially its true power output. Apparent brightness, on the other hand, is how bright the star appears to us from Earth, and that depends heavily on distance, as well as on the star's specific spectrum of radiation. So let's apply this to our Doradus. On the surface, our Doradus is immense. Its swollen, gaseous envelope gives it a diameter roughly 370 times larger than the Sun. With such an extended atmosphere, you might expect it to light up the night sky like a beacon. But here's the catch: our Doradus is a red giant, a star in a late stage of its life cycle, radiating much of its energy in the infrared part of the spectrum rather than in visible light. Our eyes are not sensitive to infrared, which means that much of our Doradus's true luminosity is essentially invisible to us. The energy is there, flooding space with radiation, but our eyes only catch a fraction of it. As a result, when we look up, our Doradus appears faint. Its visual magnitude fluctuates between about magnitude 4.8 and 6.6 because it's also a variable star, something we'll discuss in depth later. That range means that sometimes, under very dark skies, it's barely visible at the threshold of naked eye detection. To put that in perspective, the faintest stars visible to most people under ideal conditions are around magnitude 6. By contrast, the bright star Sirius shines at a dazzling magnitude -1.46, hundreds of times brighter to the human eye. This is why brightness can be so deceptive. Sirius, the brightest star in our night sky, is only about twice the size of the sun. Betelgeuse, which shines vividly orange-red in Orion, is larger and intrinsically brighter than R Doradus, but its greater distance still dims its apparent brilliance somewhat. Meanwhile, R Doradus, despite being gargantuan, is subdued to the eye simply because so much of its light falls outside the visible spectrum and because it sits in a part of the sky not well known for bright, standout stars. The irony here is profound. When astronomers look at R Doradus with instruments that can detect infrared radiation, the star absolutely glows. In fact, R Doradus is one of the brightest infrared sources in the entire sky. This makes it an essential target for infrared telescopes and studies. But to the human eye, which evolved to see visible wavelengths optimized for sunlight, it's just a faint, unassuming point. If our eyes were sensitive to infrared light, R Doradus would not be a forgettable star. It would be one of the most dazzling features of the heavens. This difference between size and apparent brightness also highlights an important teaching moment about astronomy in general. The sky doesn't tell us everything just by looking at it. Two stars of the same brightness might be wildly different in size, distance, or energy output. A faint star could actually be a colossal red giant, and a bright star might be relatively small but very close to Earth. This is exactly why astronomers rely on measurements, spectra, and careful study to understand what stars really are. So when you look at R Doradus, what you're really seeing is a cosmic disguise. Its faint glow tells you very little about the true giant lurking behind that light. It's almost as though the star is hiding in plain sight, its massive body cloaked by the limitations of human vision. For those who know the truth, that faint speck of light becomes something extraordinary, a reminder that the universe doesn't always reveal its grandest treasures easily. In summary, R Doradus demonstrates that size does not equal brightness. It may not rival Sirius, Vega, or Betelgeuse in brilliance, but it surpasses most of them in sheer physical dimensions. It is a giant humbled by the quirks of physics and human biology, invisible in its true glory yet monumental in its reality. The night sky is full of such paradoxes, and R Doradus is one of the most fascinating examples. When we talk about the size of R Doradus, we're stepping into a realm of proportions that stretch the imagination far beyond what most of us can comfortably picture. Our everyday sense of scale, measured in kilometers, mountains, or even planetary diameters, simply isn't enough to grasp what it means for a star to be large. So, to understand the enormity of R Doradus, we have to compare it to something familiar, our very own Sun. The Sun is already unimaginably vast compared to anything on Earth. Its diameter is about 1.39 million kilometers, 864,000 miles. That's big enough that about 109 Earths could be lined up across its face, and over 1.3 million Earths could fit inside its volume. The Sun dominates our solar system so completely that it accounts for more than 99.8% of all the mass. To us, it feels like the ultimate giant, the centerpiece of everything we know. And yet, compared to R Doradus, our Sun looks almost insignificant. Astronomers estimate that R Doradus has a diameter roughly 370 times larger than the Sun. That translates to a star with a diameter of about 515 million kilometers, 320 million miles. To put this in perspective, that's so enormous that if R Doradus replaced our Sun at the center of the solar system, its bloated surface would extend far beyond Mercury, Venus, and even out to Earth's orbit, nearly swallowing our planet whole. This isn't just big, it's staggering. Imagine the Sun, already so huge that 1 million Earths could fit inside, multiplied hundreds of times over. The sheer volume of R Doradus is enough to make the solar system feel claustrophobic. If the Sun were a basketball, then R Doradus would be a sphere as wide as a 40-story building. The difference is not just impressive, it's almost absurd. Another way to think about this is to consider the speed of light. Light travels incredibly fast, about 300,000 kilometers per second. It takes just over 8 minutes for sunlight to reach Earth. But if you started at one edge of R Doradus and tried to cross to the other side at the speed of light, it would take more than 28 minutes. That's right, light itself would need nearly half an hour to cross the star's diameter. In contrast, it only takes about 4.6 seconds for light to cross the Sun. That gives you some sense of just how much larger R Doradus is. Now, here's the twist. R Doradus is not particularly massive compared to other stars. Its estimated mass is only about 1.5 times that of the Sun. That means it's not dramatically heavier than our Sun, but it has ballooned into an enormous, diffuse red giant. Most of its volume is actually tenuous gas. Its outer layers are puffed out into a vast, extended atmosphere. It's not a dense ball of matter but more like a gigantic, glowing cloud. This is why, despite its colossal size, its gravity at the surface would not feel as crushing as you might expect. What's even more incredible is that stars like R Doradus achieve this size in the later stages of their evolution. Once a star runs out of hydrogen in its core and begins to fuse helium or heavier elements, its outer layers expand dramatically. In essence, R Doradus is a Sun-like star that has entered its retirement phase, swelling to many times its original size. The expansion is temporary, though it won't last forever. So when we say R Doradus is 370 times larger than the Sun, we are pointing to one of the most mind-bending contrasts in astronomy. A star that is only slightly more massive than the Sun but spread out to such an extent that it dwarfs our entire solar system. It's a reminder that size in astronomy doesn't always follow intuitive rules. Mass, luminosity, and volume can play out in strange ways as stars evolve, and R Doradus is one of the clearest examples of that. For the average observer, it's almost impossible to imagine such an enormous object being so faint in the sky. But that's exactly what R Doradus is, a star that could engulf Earth if it were placed in the Sun's position, yet to our eyes, it appears no brighter than an ordinary star. This paradox only makes it more fascinating. To truly appreciate the enormity of R Doradus, it's not enough to simply quote numbers. Millions of kilometers, hundreds of times larger than the Sun, or half an hour for light to cross its diameter. Numbers can impress us, but they often fail to sink in. What really makes its size tangible is imagining what it would mean if R Doradus were placed right where our Sun is now, at the center of the solar system. That's when its staggering scale really hits home. If R Doradus were swapped with the Sun, its swollen outer layers would extend far beyond the orbits of Mercury and Venus. But it wouldn't stop there, it would swell almost all the way to Earth's orbit. That means our home planet would be skimming the very edge of its outer atmosphere, if not swallowed entirely. Instead of orbiting safely around the Sun at a comfortable distance of 150 million kilometers, Earth would be precariously close to being engulfed by a vast, glowing surface of stellar plasma. In fact, depending on the exact measurement of R Doradus's ever-changing diameter, our planet might not survive at all. Think about what that would look like from Earth. The Sun, which today appears as a bright but modest disk about half a degree wide in the sky, would suddenly balloon outward until it filled nearly the entire sky. There would be no day and night as we know them, just an endless, blazing expanse of red-orange light. The Earth's atmosphere and oceans would be stripped away, and our planet would quickly become uninhabitable, if it even remained intact at all. From our perspective, the sky would be nothing but star. This visualization doesn't just emphasize R Doradus's sheer size, it also underscores the delicate balance of our solar system. The Sun is already exactly the size it needs to be for life to exist here. A small change in its size or output could drastically alter conditions on Earth. Now imagine replacing it with a star hundreds of times larger. That balance would be obliterated instantly. R Doradus shows us just how lucky we are to orbit a stable, medium-sized star that provides the right conditions for life. Now let's scale this idea outward. If R Doradus stretched to Earth's orbit, then all the inner planets, Mercury, Venus, and Earth, would be either consumed or vaporized within its searing outer atmosphere. Mars would orbit just beyond its swollen edge, but even there, the conditions would be extreme. The asteroid belt would mark the first truly safe distance from the star. Everything we know about our solar system, its structure, its planets, its rhythms, would be completely transformed by a star of this scale. This is the power of perspective. Suddenly, the numbers aren't abstract anymore. You don't just hear 370 times the Sun's diameter. You see Earth itself hanging on the brink of annihilation, orbiting at the razor's edge of survival. You see Mercury and Venus utterly gone, swallowed whole by the star's immense body. You see the solar system remade in the image of a red giant, where worlds that once thrived are now reduced to cinders. It also helps us understand why stars like R Doradus, though fascinating, are not conducive to life-bearing systems like ours. Red giants are unstable, variable, and short-lived compared to stars like the Sun. They may host planets, But those worlds face constant danger from the star's expanding atmosphere, fluctuating radiation, and eventual collapse. In a way, R Doradus is both awe-inspiring and a reminder of cosmic mortality. Even stars like our Sun will eventually grow into red giants and perhaps engulf the inner planets. One day, Earth too may share the fate that R Doradus threatens to impose if it were placed in our neighborhood. In summary, putting R Doradus into the solar system brings its unimaginable scale into vivid relief. It's not just big, it's big enough to rewrite the entire architecture of our planetary system. Its fiery surface would nearly reach Earth's orbit, turning our world into either a furnace or an afterthought. This exercise in perspective transforms R Doradus from an abstract point of light in Dorado into a cosmic leviathan, one that forces us to confront just how small and fragile our own world really is. When we describe R Doradus, one of the most important things to understand about its nature is the kind of star it is. R Doradus is not a youthful, stable star like our Sun, nor is it one of the massive, short-lived monsters destined for a violent supernova. Instead, it belongs to a fascinating and dramatic class of stars known as red giants, stars that have left the prime of their lives behind and are entering the twilight stages of stellar evolution. To put this in context, let's first consider what it means for a star to be main sequence, which is where most stars, including our Sun, spend the majority of their lifetimes. During this phase, a star steadily fuses hydrogen into helium in its core, generating energy that balances against the crushing pull of gravity. For a medium-sized star like the Sun, this balance can last billions of years, providing stability and a steady glow. But eventually, the hydrogen in the core runs out. When that happens, the delicate equilibrium is lost. The star's core contracts under gravity, heating up, while the outer layers expand outward dramatically. The star swells to many times its original size, its surface cools compared to its hotter youth, and its color shifts toward the red end of the spectrum. This transformation marks the birth of a red giant. R Doradus is precisely in this stage. It is a relatively low to intermediate mass star, not terribly different from our Sun in mass, but far older in its life cycle. Having burned through the hydrogen in its core, it has expanded into a swollen, luminous giant. Its surface temperature is much cooler than the Sun's, which is why it appears reddish rather than white or yellow. Red giants like R Doradus radiate enormous amounts of energy, not because they are hotter, in fact, they are cooler at the surface, but because their surface area is so vast. Imagine a fire that burns cooler but grows to hundreds of times its previous size. The total output can still be immense. What makes red giants like R Doradus particularly fascinating is that they are unstable and dynamic. Unlike main sequence stars, which enjoy long eras of stability, red giants are in constant flux. Their outer layers expand and contract, their brightness varies, and their atmospheres become extended and tenuous. It's a kind of stellar old age, where the star is no longer in balance but in the throes of transformation. R Doradus is classified more specifically as an asymptotic giant branch, AGB, star. This is a late phase in stellar evolution that occurs after a star has already become a red giant once and undergone helium fusion in its core. In the AGB phase, the core is composed mainly of carbon and oxygen, while shells of helium and hydrogen around it undergo periodic bursts of fusion. These processes cause the star to puff up, shed material, and pulse in brightness, behaviors we can observe from Earth. For astronomers, this makes R Doradus a kind of living laboratory. It shows us what will eventually happen to stars like our Sun billions of years from now. Our Sun will follow a very similar path, expanding into a red giant, swallowing the inner planets, and then eventually casting off its outer layers to leave behind a white dwarf. By studying R Doradus, we are, in a sense, peering into our own star's distant future. And let's not forget the poetic side of this transformation. The red giant phase is both destructive and creative. On one hand, stars like R Doradus swell so massively that they destabilize their planetary systems, destroy nearby worlds, and lose their once stable shine. On the other hand, this phase is when stars begin producing and releasing heavier elements, carbon, oxygen, and others, that will eventually seed future generations of stars and planets. Without red giants, the universe as we know it would lack many of the ingredients necessary for life. So, when we call R Doradus a red giant, we're saying more than just that it's a big, red star. We're recognizing that it's in a critical, transitional stage of life. It's nearing the end of its stellar journey, no longer stable, but not yet gone. Its bloated size, its cooler glow, and its restless variability are all hallmarks of this final act. For astronomers, R Doradus is not only a spectacle, it's a key piece of the puzzle in understanding how stars age, die, and recycle their material into the cosmos. In short, R Doradus is a red giant in the later stages of stellar evolution. It is a reminder that stars are not eternal. They are born, they live, and they die, following cycles that shape galaxies and even life itself. For us, it's a cosmic mirror, showing us the fate that one day awaits our sun and perhaps even our world. One of the most intriguing characteristics of R Doradus is that it doesn't shine with a steady, unchanging light. Instead, it belongs to a special class of stars known as variable stars. That means its brightness, as seen from Earth, fluctuates over time. Unlike our sun, which maintains a fairly consistent output of light and energy, R Doradus appears to breathe, growing brighter and dimmer in cycles that reflect the turbulent processes happening deep inside it. So what does it mean to call a star variable? Essentially, a variable star is one whose apparent magnitude changes, either because of internal processes, external influences, or a combination of both. In the case of R Doradus, the variability is intrinsic. That is, the changes come from within the star itself, not from something passing in front of it or obscuring it. To the human eye, this variability might not always be obvious. R Doradus typically hovers around magnitude 4.8 to 6.6, sometimes bright enough to spot under dark skies, other times fading to the very threshold of naked eye visibility. That range may not seem dramatic compared to stars like Mira, another famous red giant variable that can fade from naked eye brightness to invisibility, but it's still significant. For astronomers, these fluctuations are clues that reveal what's happening in the star's interior. The variability of R Doradus is tied directly to its pulsations. As a red giant, its outer layers are unstable and prone to rhythmic expansions and contractions. Imagine a balloon inflating and deflating slowly, except on a scale so vast it defies comprehension. During the expansion phase, the star's outer layers spread outward, its surface area increases, and its brightness as seen from Earth rises. Then gravity pulls the layers back inward, the star contracts, and its brightness diminishes. This cycle repeats over and over, creating the observed variations in light. Astronomers classify R Doradus as a semi-regular variable star, which means it doesn't have the perfectly predictable rhythm of a Cepheid variable, for example, but it still shows fairly consistent cycles. In fact, its dominant period is about 332 days, meaning that roughly every 11 months, it goes through a noticeable cycle of brightening and dimming. However, because it's semi-regular, those cycles aren't perfectly precise. There can be variations in timing and amplitude, making its light curve more complex than a simple repeating pattern. This variability is more than just an astronomical curiosity, it's a powerful scientific tool. By studying the light fluctuations of stars like R Doradus, astronomers can infer details about their internal structure, their atmospheres, and their evolutionary stages. Variable stars act almost like cosmic seismographs, their pulsations providing data about what's going on beneath the surface. For R Doradus in particular, its variability helps confirm that it is an asymptotic giant branch, AGB, star, undergoing unstable burning in shells around its core. From a stargazer's perspective, the variability of R Doradus is also a reminder that the heavens are not static. Many people assume the stars are fixed, unchanging points of light. But stars are living, dynamic entities. They change on timescales ranging from hours to millennia, and with R Doradus, you can actually observe those changes within a human lifetime. Over months, you could watch it grow brighter, then dimmer, then brighter again, a stellar heartbeat that echoes across hundreds of light years. It's also fascinating to note how R Doradus compares to other famous variable stars. For instance, Mira, the prototype of Mira-type variables, has a far more dramatic range in brightness, swinging between magnitude 2 and magnitude 10. Betelgeuse, another red giant, is also variable, and its recent dimming episode in 2019 to 2020 captivated astronomers and the public alike, sparking speculation about an imminent supernova. R Doradus doesn't attract that level of attention because its fluctuations are more modest, but they're still deeply important scientifically. In summary, R Doradus is a variable star whose brightness changes over time due to pulsations in its extended atmosphere. It doesn't shine steadily like our Sun but instead waxes and wanes, reflecting the restless processes of a red giant near the end of its life. These fluctuations aren't just fascinating to watch, they're windows into the physics of stellar interiors, offering astronomers vital clues about how stars live and die. For the rest of us, they remind us that even the stars we think of as eternal and constant are, in truth, alive with motion and change. The question of why R Doradus varies in brightness takes us deep into the heart of what it means to be a red giant star nearing the final chapters of its existence. On the surface, it might seem puzzling. Why doesn't it simply shine with a steady light, like our Sun does? The answer lies in the star's pulsations, immense, slow-motion cycles of expansion and contraction that cause its light output to change over time. Let's start with the basics of stellar balance. A star spends most of its life in equilibrium, with two competing forces locked in a cosmic tug-of-war. On one side, the gravity of the star tries to pull all of its matter inward, collapsing it toward the core. On the other side, the radiation pressure from nuclear fusion pushes outward, resisting collapse. When those two forces are in balance, a star shines with steady brightness. That's why our Sun has remained so stable for billions of years. But in a star like R Doradus, this balance has been disrupted. The core has exhausted its hydrogen fuel and has shifted to fusing helium and heavier elements in shells around a dense carbon-oxygen core. These fusion processes don't proceed smoothly. Instead, they occur in bursts or pulses, causing sudden changes in the energy output. When the outward radiation pressure temporarily overwhelms gravity, the star's outer layers expand. As they expand, they cool, and the star's brightness, as seen in visible light, can actually shift. Then gravity reasserts itself, pulling the outer layers back inward, and the cycle begins again. Think of it like a giant cosmic breathing process. R Doradus literally swells and contracts over timescales of months. During the swelling phase, the star becomes larger, its surface area increases, and its brightness can rise. During contraction, the outer layers pull inward, reducing the star's size and altering the way its light escapes, which makes it dimmer to observers on Earth. These pulsations are enormous in scale. The outer layers of R Doradus can move hundreds of millions of kilometers in and out during a single cycle. This isn't just a surface phenomenon, it's tied directly to the star's internal structure. As energy builds up in the fusion shells, it creates instabilities that ripple outward, setting the whole outer atmosphere into motion. The gases in the atmosphere are not uniform or tightly bound, so they respond dramatically to even small changes in pressure. Imagine trying to control a massive balloon filled with turbulent gases. That's essentially what's happening to R Doradus on a cosmic scale. Another factor contributing to the variability is the star's temperature changes during these pulsations. As the outer layers expand, they cool, shifting more of the star's light output into the infrared range, where our eyes can't detect it. This makes the star look dimmer even though its total energy output might still be high. When the layers contract, the surface heats slightly, shifting more energy back into the visible spectrum, and the star brightens again. This combination of expansion, contraction, and temperature shifts creates the semi-regular pattern of variability we see from Earth. R Doradus is classified as a semi-regular variable star, which means its pulsations are not as predictable as some other types of variable stars, like Cepheids. Its primary pulsation period is around 332 days, but because of the complex physics in its extended atmosphere, its brightness variations don't follow a perfectly uniform rhythm. Sometimes the cycles are stronger, sometimes weaker, and sometimes slightly off in timing. This irregularity makes stars like R Doradus both challenging and fascinating to study. The variability also has profound consequences for the star's fate. With every pulse, the outer layers are not only moving but also being weakened. Over time, these pulsations contribute to the loss of mass. Material from the star's atmosphere is expelled into space, carried away by stellar winds. This mass loss is an essential part of the red giant phase and will eventually lead R Doradus to shed much of its outer envelope, forming a planetary nebula. In a very real sense, the pulsations that cause its brightness to vary are also the mechanisms by which it prepares for its death. For astronomers, the fact that R Doradus varies in brightness is like having a direct window into the internal workings of a giant star. By carefully tracking these changes in light, scientists can infer details about the star's size, its pulsation modes, and the processes occurring in its fusion shells. The light curve of R Doradus, a graph of its brightness over time, is essentially the star's heartbeat, telling us how it's living out the final chapters of its existence. To the casual observer, R Doradus may just look like a faint star that sometimes grows a little brighter or dimmer. But behind that simple flicker lies a profound truth. This is a star literally in motion, swelling and contracting, reshaping itself as it struggles against gravity and prepares to cast off its outer layers. Its variability is not a flaw or a curiosity. It is the very essence of what it means to be a red giant on the brink of transformation. When we talk about the distance to R Doradus, we enter one of the most awe-inspiring aspects of astronomy. The idea that the light we see in the night sky has traveled vast cosmic gulfs of space and time just to reach our eyes. R Doradus is not in our immediate neighborhood of stars, like Alpha Centauri or Sirius. Instead, it lies at an impressive distance of about 200 to 230 light-years away from Earth. Now, to grasp what that means, let's first recall what a light-year is. A light-year is the distance that light, moving at about 300,000 kilometers per second, or 186,000 miles per second, travels in 1 year. That comes out to almost 9.5 trillion kilometers, or about 5.9 trillion miles. So when we say R Doradus is 200 light-years away, we're talking about a distance of nearly 1.9 quadrillion kilometers, a number so enormous it's practically beyond human imagination. And if we stretch it to 230 light-years, that's closer to 2.2 quadrillion kilometers. This means the light that enters your eye when you look at R Doradus on a clear night began its journey more than 2 centuries ago. In other words, we are not seeing R Doradus as it exists today. We're seeing it as it was roughly in the late 1700s to early 1800s. By the time the photons from its surface travel across interstellar space and reach Earth, generations of human history have already unfolded. Wars have been fought, nations have risen and fallen, scientific revolutions have come and gone, and yet the light keeps moving steadily toward us, unaffected by the passage of human time. That distance also has a profound effect on how R Doradus appears in our sky. Remember, it's the largest star visible to the naked eye, but it is not particularly bright compared to other naked eye stars. If R Doradus were closer, say, as close as Sirius, which is just over 8 light-years away, it would be dazzling, far outshining almost everything else in the night sky. Its faintness is not a sign of weakness but a simple consequence of how far away it sits. Distance diminishes brightness, spreading the star's light across an expanding sphere of space until only a faint trickle reaches Earth. Interestingly, the relatively close distance of R Doradus, in cosmic terms, at least, is what makes it such a valuable target for astronomers. At 200 to 230 light-years away, it's one of the nearest asymptotic giant branch, AGB, stars we can study. Many red giants are much farther away, making them harder to observe in detail. R Doradus, by contrast, is close enough that astronomers can actually resolve its disk using special techniques like interferometry, something that's nearly impossible for most stars. In other words, its proximity allows us to study the extended atmosphere of a red giant up close, almost as if we're peering at its surface directly. The distance to R Doradus is also important for understanding its physical scale. By combining measurements of its apparent size in the sky, its angular diameter, with its distance, astronomers can calculate its true size in kilometers and compare it to our Sun. If the distance were miscalculated, our estimates of its diameter and luminosity would also be off. Thanks to precise data from missions like Gaia, we now have a much more accurate handle on its distance, putting it firmly in that 200 to 230 light-year range. To put this distance in perspective, consider our nearest stellar neighbor, Proxima Centauri, which is only 4.24 light-years away. R Doradus is roughly 50 times farther away than that. Yet, despite being so much farther, it still manages to appear in our naked eye sky, something Proxima Centauri doesn't manage, since it's too faint to be seen without a telescope. That fact alone tells us just how gigantic and luminous R Doradus truly is. For a star to be faintly visible across hundreds of trillions of kilometers, its intrinsic brightness must be staggering. But let's bring it back to Earth for a moment. If you step outside on a clear night in the southern hemisphere and catch a glimpse of R Doradus, remember this: the tiny pinpoint of light you see is an echo from centuries past. That light began its journey when people on Earth were sailing wooden ships, when electricity was still a curiosity, and when telescopes were primitive instruments compared to today's observatories. It has traveled through the cold, empty void of interstellar space, across unimaginable distances, just to meet your eyes for the briefest instant before moving on. So when we say a Doradus is 200 to 230 light-years away, it's not just a number. It's a reminder of how vast our universe is, how long light takes to travel, and how deeply connected we are to the cosmos through the very photons that reach us. Every glance at this distant red giant is a look backward in time, a direct experience of the universe's grand scale. When we say that a Doradus is 200 to 230 light-years away, we're not just giving a measurement of distance. We're also making a profound statement about time. Light doesn't travel instantly. It moves at a finite speed of about 300,000 kilometers per second, or 186,000 miles per second. While that's unimaginably fast by human standards, the universe is so vast that even light takes years, centuries, or millennia to cross the distances between stars. So when we look at a Doradus tonight, we're not seeing it as it exists at this very moment. Instead, we are seeing it as it was more than 2 centuries ago. The photons that enter your eye began their journey long before the modern world existed. In fact, if we place it at about 230 light-years away, the light you see now would have left a Doradus sometime in the late 1700s. That was a time when the world was a very different place. The American Revolution had just ended, the French Revolution was brewing, and the first industrial machines were beginning to transform human society. When that light left the surface of a Doradus, people were using quill pens, riding horses, and navigating oceans without engines. This time delay is one of the most fascinating aspects of astronomy. Every star in the night sky is, in a sense, a time capsule. The farther away the star, the further back in time we're looking. With nearby stars like Alpha Centauri, the delay is only a few years, so we're essentially seeing them in their fairly recent past. But with our Doradus, we're stepping back 2 full centuries in human history. That means the star we see is not the star as it exists right now. If some dramatic event happened to a Doradus today, like it suddenly dimming dramatically or even beginning to shed more of its layers, we wouldn't know about it until over 200 years from now. This leads to a strange but beautiful truth. We can never see the universe as it is. We can only see it as it was. The night sky is a grand tapestry woven not in real time, but in light delayed by unimaginable journeys. Every star is telling us a story from the past, and when we piece those stories together, we reconstruct the history of the cosmos itself. In this sense, a Doradus isn't just a star, it's a messenger from the 18th century, whispering across space to tell us what it was doing back then. It also highlights the limits of our human perspective. To us, 2 centuries feels like a long time. Empires rise and fall, generations pass, technologies revolutionize our world. But for a star like a Doradus, centuries are nothing more than brief moments in its multimillion or billion-year lifetime. In other words, while we see it as it was 200 years ago, the star itself hasn't changed much in that span compared to its colossal evolutionary timescale. Its pulsations, variability, and gradual mass loss continue on, but to the star, those centuries are a blink of an eye. Still, the concept of looking back in time is deeply profound. It means that astronomy is not only about space but also about history. When astronomers point their telescopes at distant galaxies, they're looking millions or even billions of years into the past, seeing galaxies as they were when dinosaurs roamed Earth or even before Earth itself existed. With our Doradus, we don't have to go that far back to feel the weight of cosmic time. Just the fact that the light we see tonight left before our great-great-great-grandparents were born is enough to inspire awe. Think of it this way. When you look up at a Doradus, you're connecting with a specific moment in human history. Imagine an astronomer in the 18th century, perhaps William Herschel scanning the skies in England, or astronomers in France or Spain charting southern constellations. The light they saw from a Doradus was hundreds of years older still. And the light we see tonight will keep traveling past Earth, perhaps striking some alien planet far in the future, where another being might gaze up and wonder about the faint red star in their sky. So what does it mean that a Doradus is 200 to 230 light-years away? It means that when we look at it, we are looking into the past. It means that our connection to the stars is not instantaneous, but stretched across time. It means that every starlit night is an archive of history, preserved in photons that have traveled longer than the lifespan of nations just to reach us. And perhaps most importantly, it reminds us of our place in the universe. Tiny creatures bound to a single planet, but capable of peering into both space and time with nothing more than our eyes. R Doradus, in its faint glow, carries with it a story from centuries ago, a reminder that the cosmos is both vast and ancient, and that to look up at the stars is to gaze into the deep history of creation itself. When we begin to compare R Doradus with other famous stars, one name immediately comes to mind: Betelgeuse. Betelgeuse is perhaps the most iconic red supergiant in the sky, a star so massive and brilliant that it has fascinated astronomers and stargazers for centuries. And yet, while R Doradus is the largest star visible to the naked eye, Betelgeuse is the one that steals most of the attention. Why? The difference comes down to distance and brightness. Betelgeuse shines brilliantly in the constellation of Orion, one of the most recognizable constellations in the night sky. It marks the shoulder of Orion and is a fiery, reddish-orange beacon that almost everyone has noticed at some point, even if they didn't know its name. At its brightest, Betelgeuse reaches a magnitude of about 0.4, making it one of the 10 brightest stars in the sky. By contrast, R Doradus hovers around magnitude 5 to 6, often so faint that you need truly dark skies and sharp eyesight to pick it out. So here's the paradox. R Doradus is larger than Betelgeuse in terms of apparent size in our sky, yet it looks much dimmer. How is that possible? The key lies in the fact that Betelgeuse is far more luminous than R Doradus. It pumps out vastly more energy, making it one of the most radiant stars known. The difference comes from the fact that Betelgeuse is a red supergiant, while R Doradus is a red giant. Both are stars in late stages of life, but Betelgeuse began with far more mass and has followed a more violent and energetic evolutionary path. Now let's consider distance. Betelgeuse lies about 640 light-years away, nearly 3 times farther than R Doradus. That means the photons we see from Betelgeuse tonight began their journey in the 14th century, long before telescopes or even the Renaissance had begun. Despite being much farther, Betelgeuse is so luminous that it still easily outshines R Doradus by a staggering margin. In fact, if Betelgeuse were placed at the same distance as R Doradus, just 200 to 230 light-years away, it would blaze as one of the brightest stars in the entire night sky, outshining almost everything except the Moon and a handful of planets. But this contrast also highlights why R Doradus is so special to astronomers. While Betelgeuse commands attention with its dazzling brilliance and dramatic variability, it's much harder to study in fine detail because it's so far away. R Doradus, on the other hand, is one of the closest red giants to Earth. Its proximity allows astronomers to resolve its disk, study its atmosphere, and measure its pulsations with far greater precision than is possible for Betelgeuse. In this sense, R Doradus is a kind of nearby laboratory for red giant physics, while Betelgeuse is the spectacular but more distant showcase of red supergiant behavior. There's also a difference in fate. Betelgeuse is massive enough that it will one day end its life in a supernova explosion, an event so bright it may even be visible during the daytime. When that happens, it will briefly outshine the entire galaxy. R Doradus, by contrast, is not massive enough for such a violent end. Its death will be quieter, shedding its outer layers into a planetary nebula and leaving behind a white dwarf core. In a sense, Betelgeuse represents the extreme, fiery end of stellar evolution, while R Doradus shows the slower, gentler path that stars more like our Sun will follow. Yet despite these differences, the two stars are often compared because they represent stages in the cosmic drama of stellar aging. Both are swollen giants with extended atmospheres, both are variable stars whose brightness changes over time, and both remind us that stars are not eternal, they live, change, and eventually die. The main difference is scale and spectacle. Betelgeuse is the loud, flamboyant actor stealing the spotlight in Orion, while R Doradus is the quiet giant in Dorado, faint to the eye but massive in presence. So when we say that Betelgeuse is brighter but farther away, we're capturing an essential truth about the night sky. Brightness does not always mean size. R Doradus holds the crown as the largest star visible to the naked eye, but its faint glow means most people overlook it. Betelgeuse, meanwhile, burns in plain sight, dazzling us with its fiery brilliance, even though it's much farther from Earth. Together, they remind us that the night sky is full of contrasts: faint giants, bright supergiants, nearby laboratories, and distant spectacles, all woven into the same tapestry of stars. When we talk about the largest stars in the universe, the name that usually tops the list is UY Scuti. This colossal red supergiant, located in the constellation Scutum, has become famous for its mind-bending size. It is often described as the largest known star by radius, with estimates suggesting it is 1,700 times wider than our Sun. To put that in perspective, if UY Scuti were placed where our Sun is, its outer layers would extend beyond the orbit of Jupiter. That's a scale so vast it defies ordinary human comprehension. Now, compared to UY Scuti, R Doradus might seem modest. Its estimated diameter is about 370 times that of the Sun, absolutely gigantic by any measure, but still far smaller than the titanic proportions of UY Scuti. On paper, UY Scuti is the undisputed champion of stellar size, while R Doradus looks like a smaller giant. But here's where things get interesting. In the actual night sky as we see it from Earth, R Doradus holds a distinction that UY Scuti cannot match. The reason lies in distance. UY Scuti is located roughly 9,500 light-years away from Earth, buried deep within the Milky Way. That enormous distance makes it completely invisible to the naked eye. You'd need a telescope to have any hope of spotting it. R Doradus, on the other hand, is a near neighbor in galactic terms, just 200 to 230 light-years away. Because it's so close to us, R Doradus actually appears larger in our sky than UY Scuti or even Betelgeuse when measured by angular diameter, which is how big something looks from Earth. Think of it this way: if you hold your thumb up in front of your face, it can block out something as huge as the Moon. That's because angular size depends not only on how large an object really is, but also on how close it is to you. R Doradus is like the thumb, closer and therefore appearing larger in angular size, while UY Scuti is like a mountain far away, far larger in reality but too distant to dominate your field of view. This is why R Doradus is considered the largest star visible to the naked eye. UY Scuti may truly dwarf it in terms of physical size, but R Doradus's closeness allows it to project a bigger apparent disk in our sky than almost any other star. In fact, astronomers have measured its angular diameter to be about 0.057 arcseconds, making it one of the largest disks ever resolved for a star outside our solar system. UY Scuti, by comparison, has such a tiny angular size due to its distance that it remains a faint blur, even with powerful instruments. There's also another important factor: the uncertainties in measuring giant stars. Stars like UY Scuti and R Doradus don't have solid, sharply defined surfaces. Instead, they have extended, fuzzy atmospheres that gradually thin out into space. This makes it extremely difficult to say exactly where the edge of the star lies. As a result, estimates of UY Scuti's size vary considerably depending on how its atmosphere is modeled. Some studies have even suggested it might not be quite as enormous as early estimates claimed. By contrast, R Doradus is close enough that astronomers can measure it with much greater precision, making it one of the best-studied giants of its kind. So while UY Scuti is often labeled the largest star known, its remoteness keeps it out of sight and out of reach for direct observation. R Doradus, though smaller in absolute terms, becomes far more relevant for us because it's visible without a telescope and because its proximity makes it a natural laboratory for studying the late stages of stellar evolution. To put it another way, UY Scuti is the giant that exists mostly in numbers and calculations, while R Doradus is the giant we can actually see. That's what makes R Doradus special. It's not just a statistic buried in an astronomical database. It's a real, faint point of light in the night sky, a star that connects the abstract enormity of stellar physics with the tangible experience of looking up at the heavens with our own eyes. So the comparison between UY Scuti and R Doradus highlights two sides of astronomy: the absolute scale of the cosmos and the human perspective of the night sky. On the one hand, we marvel at UY Scuti, a star so enormous it stretches our imagination. On the other hand, we appreciate R Doradus, the largest star that we, as humans standing on Earth, can directly see. Together, they remind us that the universe is filled with both the distant unimaginable and the near, observable wonders that we can connect to with our own senses. When we turn our attention to the atmosphere of R Doradus, we enter one of the most fascinating and unusual aspects of this red giant star. Unlike our Sun, which has a relatively compact and sharply defined surface, R Doradus has a thick, extended, and diffuse atmosphere that makes its outer layers more like a vast, hazy cloud than a neat, glowing sphere. This is partly a consequence of its sheer size. At nearly 370 times the diameter of the Sun, the surface gravity of R Doradus is incredibly weak compared to smaller stars. On Earth, gravity keeps our atmosphere tightly bound to the planet. On the Sun, intense gravity keeps its plasma compressed into a brilliant photosphere. But on R Doradus, the pull of gravity at the star's surface is so feeble that its gases are only loosely held in place. As a result, the star's outer layers balloon outward, forming an atmosphere that is not only enormous in scale but also extraordinarily tenuous and unstable. The atmosphere of R Doradus is so extended that it challenges astronomers to even define where the star ends. Unlike the Sun, which has a well-defined photosphere we can measure, R Doradus has a fuzzy boundary where the atmosphere gradually thins out into interstellar space. This makes determining its exact size difficult. Different wavelengths of light may suggest different diameters, because the atmosphere glows or absorbs differently depending on the layer you're probing. Within this bloated envelope, the star's gases are constantly in motion. Convection currents, giant plumes of hot plasma rising and falling, dominate its surface. These are similar in principle to the granules on the Sun's surface, but on R Doradus, they are unimaginably larger. Individual convection cells could span distances comparable to the Earth-Moon system, creating vast hot spots and cooler patches that shift over time. These motions contribute to the star's variability and help drive the stellar winds that gradually strip material away from its outer layers. The composition of the atmosphere also reveals the chemistry of a star in its twilight years. R Doradus, like other asymptotic giant branch (AGB) stars, has a rich atmosphere filled with molecules that cannot survive in the hotter conditions around smaller stars. Observations have revealed the presence of water vapor, carbon monoxide, and silicon monoxide in its extended layers. Dust grains also form in the cooler outer reaches of the atmosphere, creating the building blocks that will one day be expelled into interstellar space and recycled into future stars and planets. This extended atmosphere is also why R Doradus shines so strongly in the infrared. Much of its energy doesn't come through as visible light, but instead emerges at longer wavelengths, where astronomers can study the molecular and dusty environment in greater detail. Infrared telescopes like the Very Large Telescope Interferometer, VLTI, in Chile or even the James Webb Space Telescope are particularly well suited to probing this kind of star. Another fascinating aspect of R Doradus's atmosphere is its pulsations. As the star expands and contracts in its semi-regular cycles, the atmosphere responds dramatically, swelling and shrinking along with the star. These pulsations can drive shockwaves through the atmosphere, temporarily heating or cooling regions, and further complicating the picture of what a Doradus looks like. From one phase of its pulsation cycle to another, its atmosphere can appear more compact or more extended, changing how astronomers measure its size. To give some perspective, imagine standing at the edge of a Doradus, if such a thing were possible. You wouldn't see a crisp, glowing surface like you do with the Sun. Instead, you'd find yourself immersed in a hazy, semi-transparent ocean of gas and dust stretching out for hundreds of millions of kilometers. The surface would be more like a fuzzy transition, a twilight zone where the atmosphere grows thinner and thinner until it finally fades into the blackness of space. This strange, thick, and unstable atmosphere is not just a curiosity, it's central to the star's fate. Over time, R Doradus will shed more and more of this gaseous envelope into space, enriching the galaxy with carbon, oxygen, and dust. These materials will drift across interstellar space, eventually merging into the clouds that form new stars, planets, and perhaps even life itself. The very atoms in our bodies owe their existence to processes happening in atmospheres like that of R Doradus. So when we talk about the atmosphere of R Doradus, we're describing a truly alien environment, an extended, turbulent, molecule-rich envelope that makes the star appear as much like a nebula as a point of light. It's a place of constant motion, chemistry, and mass loss, a reminder that even in its fading years, a star plays a vital role in the cosmic cycle of creation. One of the most fascinating aspects of R Doradus is the way it shines, not primarily in the visible spectrum that our eyes detect, but strongly in the infrared part of the spectrum. This is a common trait of red giants and asymptotic giant branch (AGB) stars, but R Doradus is an especially compelling example because of its proximity and enormous size. Its infrared glow reveals secrets about the star that cannot be discerned from visible light alone. The reason R Doradus emits so strongly in the infrared is directly tied to its surface temperature and extended atmosphere. Unlike the Sun, which has a surface temperature of about 5,500 degrees Celsius and radiates most of its energy in visible light, R Doradus has a cooler surface, roughly 2,740 degrees Celsius. Cooler stars emit most of their energy at longer wavelengths, meaning the light they produce is shifted into the red and infrared portion of the spectrum. In fact, much of the star's total energy output is invisible to the human eye and can only be detected by specialized infrared instruments. This infrared glow provides astronomers with a wealth of information about the star's properties. For instance, the extended atmosphere of R Doradus, rich in molecules such as water vapor, carbon monoxide, and silicon monoxide, absorbs and re-emits light in the infrared. Dust grains forming in the cooler outer layers of the star also glow in infrared wavelengths. By observing this light, astronomers can probe the composition, structure, and dynamics of the star's outer layers in far greater detail than would be possible with visible light alone. Infrared observations are especially important for measuring size and shape. Because R Doradus's outer layers are so tenuous and diffuse, its visible surface is not sharply defined. But in the infrared, astronomers can more accurately trace the photosphere of the star and see how it changes during its pulsation cycles. By combining infrared imaging with techniques like interferometry, which links multiple telescopes to simulate a much larger aperture, scientists can even resolve details of the star's atmosphere that would otherwise be completely blurred. Another reason infrared observations are crucial is that R Doradus is variable. Its semi-regular pulsations cause temperature fluctuations in the outer layers, which in turn affect the star's emission across different wavelengths. While the visible brightness might change modestly over the course of a pulsation cycle, the infrared output often shows a stronger signal, revealing the full extent of the star's pulsations and expansions. Essentially, infrared light acts as a more faithful indicator of the star's physical activity than visible light alone. The infrared glow also highlights the star's role in cosmic recycling. As R Doradus loses mass through stellar winds, the expelled gas and dust are cooler and emit predominantly in infrared. By studying this emission, astronomers can track how the star is feeding the interstellar medium, enriching it with elements like carbon and oxygen that will eventually become part of new stars, planets, and perhaps even life. In a very real sense, the infrared glow of R Doradus is a visible sign of the star contributing to the next generation of the galaxy. From a more human perspective, observing R Doradus in the infrared is like revealing a hidden side of the star. With the naked eye, it appears as a faint, modest point of reddish light in the constellation Dorado. But through infrared telescopes, it becomes a luminous, dynamic sphere, pulsating, shedding matter, and glowing with energy that we cannot perceive unaided. It's a reminder that stars have layers of complexity beyond what our eyes can see, and that the cosmos is richer and more intricate than it appears in ordinary light. Infrared observations of R Doradus have also led to some surprising discoveries. The star's extended atmosphere and circumstellar envelope are more pronounced in infrared wavelengths, and astronomers can see structures such as clumps of dust and gas being ejected into space. These observations help refine models of how red giants evolve and how they lose mass, which is a critical piece of understanding the life cycles of stars like R Doradus and the eventual formation of planetary nebulae. In short, the infrared glow of R Doradus transforms our understanding of the star. While its visible light may appear faint and modest to the human eye, its infrared emission reveals a star that is massive, dynamic, and actively shaping its environment. Through infrared light, R Doradus communicates its size, its pulsations, its extended atmosphere, and its contribution to the galaxy, providing astronomers with a rich tapestry of data about the life of a red giant in its twilight years. Studying a star like R Doradus presents a unique set of challenges for astronomers. Unlike point-like stars that appear as simple dots of light, R Doradus has a large, extended, and fuzzy atmosphere, making it difficult to measure using traditional observational methods. Its size and proximity, however, also make it an ideal candidate for advanced techniques like interferometry and multi-wavelength telescopic observations, allowing astronomers to probe the structure and behavior of a star that would otherwise remain a mystery. First, let's consider the problem. Stars are incredibly distant objects, and even the largest red giants appear tiny when projected onto the night sky. R Doradus, despite being huge, subtends only about 0.057 arcseconds in angular diameter as seen from Earth. For comparison, the Moon's angular diameter is about 1,800 arcseconds. In other words, the apparent size of R Doradus is tiny, a fraction of a pixel for most conventional telescopes. To resolve its disk and see details of its atmosphere requires extraordinary precision. This is where interferometry comes into play. Interferometry is a technique that links multiple telescopes together to simulate a much larger telescope. By combining light waves collected at different points, astronomers can achieve an effective resolution far beyond that of any single telescope. In practice, interferometers like the Very Large Telescope Interferometer, VLTI, in Chile allow scientists to measure the angular diameter of a Doradus with unprecedented precision. They can even detect asymmetries in its atmosphere, seeing how it swells, pulsates, and ejects material. Telescopes working in the infrared spectrum are also essential. As discussed earlier, our Doradus emits a significant portion of its energy in infrared wavelengths because of its relatively cool surface and extended atmosphere. Infrared telescopes can penetrate the layers of dust and gas surrounding the star, allowing astronomers to see regions that are invisible in visible light. Instruments like the VLTI's Pioneer and Amber instruments or space-based telescopes such as the James Webb Space Telescope, JWST, can observe a Doradus at these wavelengths, mapping temperature variations, measuring molecular composition, and detecting stellar winds. Using these techniques, astronomers have been able to determine not just the star's size but also its shape, surface features, and pulsation patterns. Red giants like a Doradus are not perfect spheres. Their atmospheres can be lopsided due to convection currents, rotation, and mass loss processes. Interferometry allows scientists to detect these subtleties, providing a three-dimensional view of a star that would otherwise appear as a single blurred point. Another method astronomers employ is spectroscopy. By splitting the star's light into its component wavelengths, scientists can determine the chemical composition of a Doradus's atmosphere, the velocities of gases moving in and out, and even the presence of dust grains forming in its outer layers. Spectroscopy, combined with interferometry, gives a detailed picture of the physical and chemical conditions in the star's outer atmosphere, allowing researchers to model its pulsations, mass loss, and energy output. Long-term monitoring is also crucial. Our Doradus is a semi-regular variable star, meaning its brightness changes over time as it pulsates. Continuous observations across multiple cycles help astronomers understand the timing, amplitude, and nature of these variations. By combining brightness measurements, interferometric imaging, and spectroscopic data, scientists can build dynamic models of the star, showing how it expands and contracts, how material is ejected, and how its atmosphere evolves over decades. These techniques have revealed just how complex and dynamic our Doradus really is. Its atmosphere is not a simple shell but a turbulent, shifting environment with shock waves, convection currents, and regions of dust and molecules forming and dissipating. Measuring such a star is more akin to studying a stormy, roiling ocean than a static glowing ball. Yet thanks to modern technology, astronomers can now probe these distant giants with extraordinary detail, gaining insight into a star's life in its twilight years. In summary, telescopes, interferometry, and spectroscopy are the tools that allow astronomers to study a Doradus despite its distance, fuzzy boundaries, and semi-regular variability. Through these methods, we can measure its size, track its pulsations, study its chemical composition, and even visualize the structure of its extended atmosphere. Without these advanced observational techniques, our Doradus would remain a faint, mysterious point in the southern sky. Instead, it has become a window into the late stages of stellar evolution, providing invaluable knowledge about how stars like our Sun live, pulsate, and ultimately die. Measuring a star like a Doradus may sound straightforward at first glance. After all, it's one of the largest stars visible to the naked eye, and we can observe it with sophisticated telescopes. But in reality, determining its exact size is far from simple. The primary challenge lies in the fact that a Doradus, like other red giants, does not have a sharply defined surface. Unlike a planet, which has a clear boundary between solid ground and space, a red giant gradually transitions from dense, bright plasma at its surface to tenuous gas extending millions of kilometers into space. This creates a fundamental ambiguity when astronomers try to define the star's radius. At the core of the problem is the extended, diffuse atmosphere of R Doradus. Its outer layers are not tightly bound by gravity, and as a result, the density of material decreases gradually with distance from the core. There isn't a sudden drop-off that defines a crisp edge. Instead, the star's atmosphere fades out into the surrounding vacuum, producing what scientists call a fuzzy photosphere. This is the layer from which most of the star's visible and infrared light escapes, but even this photosphere is dynamic and irregular. Different regions may have slightly different densities, temperatures, or compositions, making it difficult to pinpoint a single, definitive surface. The star's pulsations add an additional layer of complexity. As a semi-regular variable star, R Doradus undergoes cyclical expansion and contraction, with its outer layers moving in and out over months-long periods. During expansion phases, the atmosphere can stretch outward by millions of kilometers, temporarily increasing the star's apparent radius. During contraction phases, it shrinks back in. Because these pulsations are not perfectly uniform, the star's radius can vary slightly from one pulsation cycle to another. Consequently, any measurement of R Doradus's size is really a snapshot in time, which might differ depending on when and how it is observed. Another complication comes from the wavelength of light used to observe the star. R Doradus emits strongly in both visible and infrared light, but the atmosphere is optically thick at some wavelengths and thinner at others. In visible light, certain molecules and dust in the outer atmosphere can absorb or scatter radiation, making the star appear slightly smaller. In infrared, the extended gas and dust become more transparent, revealing layers farther out. This means that the measured size depends on the part of the spectrum being observed, leading to a range of estimated diameters rather than a single precise number. Observational technique also affects measurements. Interferometry allows astronomers to resolve R Doradus's disk, but even this method has limitations. The light waves coming from different parts of the star can interfere in complex ways, and modeling this interference requires assumptions about the star's atmosphere and brightness distribution. Any errors or uncertainties in these models propagate into the final size estimate. Even the best instruments can only give a range of plausible diameters rather than a perfect figure. Additionally, stellar activity such as convection currents and localized bright or dark spots can distort measurements. Red giants like R Doradus have enormous convective cells that can cover huge fractions of the star's surface. These cells are constantly moving, rising, and falling, and can temporarily alter the brightness profile of the star. If a bright convective plume is facing Earth during an observation, it can make the star appear slightly larger in that region. If a cooler area is dominant, it can appear smaller. These natural irregularities further complicate attempts to define a single true radius. The combination of all these factors, diffuse atmosphere, pulsations, wavelength dependence, instrumental limitations, and surface irregularities, means that measuring the size of R Doradus is an inherently uncertain task. Astronomers usually report a range or an average diameter, acknowledging the limitations of the observations. For example, estimates of its diameter cluster around 370 times the Sun's diameter, but this is not a fixed number. It may fluctuate slightly over time or vary depending on observational methods. Despite these challenges, the measurements we have of R Doradus are remarkably informative. They allow astronomers to model the star's mass, luminosity, and evolutionary state and to compare it with other red giants and supergiants. But the uncertainty in its size is a reminder of the complexity of real stars. Unlike idealized models, actual stars are dynamic, extended, and irregular objects, resisting simple characterization. In short, determining the size of R Doradus isn't like measuring a planet or a solid sphere. Its fuzzy, pulsating, extended atmosphere, combined with observational and spectral complexities, ensures that any estimate is approximate. Yet these measurements, even with their uncertainties, provide an extraordinary window into the physics of red giants, helping us understand their structure, behavior, and ultimate fate. The ultimate fate of R Doradus is a fascinating story of transformation, illustrating the life cycle of stars that are not massive enough to end in a supernova but are far larger than our Sun. As a red giant, R Doradus is in the late stages of stellar evolution, specifically on the asymptotic giant branch, AGB. During this phase, it has exhausted the hydrogen and helium in its core and is now burning these elements in shells surrounding an inert carbon-oxygen core. This stage is inherently unstable, and the star is slowly approaching the end of its life as it prepares to shed its outer layers. Over time, R Doradus will continue to lose mass through strong stellar winds, gradually ejecting its extended atmosphere into surrounding space. These winds are driven by a combination of factors, including the pulsations that cause the star to expand and contract, radiation pressure on dust grains formed in the outer atmosphere, and convection currents stirring the plasma. The mass loss is not a single explosive event but a gradual shedding of layers over tens of thousands to hundreds of thousands of years. As the outer layers drift away, they form a glowing shell of gas and dust known as a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. The term comes from the round, planet-like appearance of these shells when early astronomers first observed them through small telescopes. This nebula will be illuminated by the hot core of the star, which becomes exposed as the surrounding material is cleared away. The ejected gas will shine with a mixture of colors depending on the elements present: oxygen, carbon, nitrogen, and hydrogen, creating a spectacular and ephemeral display in space. The formation of a planetary nebula marks a profound transition. R Doradus will go from a massive, extended red giant to a much smaller and hotter remnant at its center. While the outer layers are being blown into space, the core itself remains intact, composed primarily of carbon and oxygen. Without enough mass to trigger a supernova, this core cannot collapse into a neutron star or black hole. Instead, it will stabilize as a white dwarf, a dense stellar remnant roughly the size of Earth but with a mass comparable to the Sun. The planetary nebula stage is relatively short-lived in cosmic terms, lasting only tens of thousands of years. Over time, the gas and dust will disperse into the interstellar medium, contributing to the cosmic recycling process that seeds new stars, planets, and even the building blocks of life. The very elements that R Doradus has produced and expelled, carbon, oxygen, nitrogen, will become part of future generations of stars, and potentially, the material from which planets like Earth may form. In this sense, the star's death is not an end but a transformation, feeding the cycle of creation throughout the galaxy. It is fascinating to consider that the dramatic variability and extended atmosphere we observe today are harbingers of this ultimate fate. The pulsations, the infrared glow, the semi-regular brightness changes, all of these are signs that R Doradus is actively reshaping itself and its surroundings in preparation for this final evolutionary stage. Each expansion and contraction of the outer layers slowly pushes material outward, contributing to the nebula that will one day surround its exposed core. From a cosmic perspective, R Doradus's fate is a story of gradual beauty rather than catastrophic destruction. Unlike massive stars that explode in supernovae, leaving behind neutron stars or black holes, R Doradus will fade gently, leaving a brilliant, short-lived nebula before settling into a quiet, long-lived white dwarf. Its material will drift through space, enriching the interstellar medium and influencing star formation in ways that are almost impossible to quantify but critical to the evolution of the galaxy. In short, the destiny of R Doradus is a testament to the life cycle of medium-mass stars. It swells into a massive red giant, sheds its outer layers to create a planetary nebula, and finally settles into a dense, cooling white dwarf. While the process is gradual and spans thousands of years, it encapsulates the essential cosmic truth that stars are not eternal. They are engines of creation, recycling matter and energy through the universe in ways that will resonate for eons. At the heart of R Doradus lies the key to its ultimate fate, the core. After the star has shed its outer layers to form a planetary nebula, the remaining core will stabilize as a white dwarf, a dense, compact stellar remnant that represents the final stage in the life of medium-mass stars like R Doradus. Understanding this transition helps us grasp both the life cycle of stars and the cosmic recycling process that fuels the galaxy. A white dwarf is fundamentally different from the active, luminous star we currently observe. Whereas R Doradus shines due to ongoing nuclear fusion in its core and surrounding shells, a white dwarf no longer produces energy through fusion. Instead, it radiates only the residual heat stored in its dense interior, gradually cooling over billions of years. Despite its relatively small size, roughly comparable to Earth, this remnant will retain a mass comparable to that of the Sun, meaning it will be incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth, emphasizing the extreme nature of these stellar remnants. The formation of a white dwarf is a natural consequence of R Doradus's mass and evolutionary path. Stars more massive than about 8 times the mass of the Sun end their lives in violent supernovae, potentially leaving behind neutron stars or black holes. R Doradus, however, is less massive. Its nuclear fusion processes will eventually cease once it can no longer fuse helium and heavier elements, leaving behind a carbon-oxygen core that is no longer able to generate energy. Gravity compresses this core until it reaches a state known as electron degeneracy pressure, a quantum mechanical effect that prevents further collapse despite the absence of fusion. This is what stabilizes the white dwarf and gives it longevity. The cooling of the white dwarf is a slow and almost imperceptible process on human timescales. Initially, the core will be extremely hot, with temperatures exceeding 100,000 degrees Celsius, radiating primarily in ultraviolet light. Over millions to billions of years, it will gradually cool, dim, and fade, eventually becoming a faint, cold, dark remnant often referred to as a black dwarf, though the universe is not old enough for any black dwarfs to exist yet. In this sense, the white dwarf represents a quiet, enduring monument to the star's life, a remnant that preserves its mass and history long after the glowing red giant has disappeared. One of the most fascinating aspects of the white dwarf stage is its role in cosmic evolution. The planetary nebula ejected by R Doradus contains heavy elements created during the star's lifetime, such as carbon, oxygen, and nitrogen. These elements disperse into interstellar space, enriching molecular clouds that will eventually form new stars, planets, and possibly life. Meanwhile, the white dwarf itself remains as a dense, slowly cooling core, a testament to the star's existence and a marker for astronomers tracing stellar evolution in the galaxy. The white dwarf phase also highlights a profound contrast between appearance and reality. R Doradus today is a massive, visually striking red giant, spanning hundreds of times the Sun's diameter. In the future, the white dwarf that remains will be tiny by comparison, roughly the size of Earth, but far denser and more enduring. It's a stark reminder that in stellar evolution, size and visibility do not always correlate with significance or longevity. The dazzling spectacle of the red giant phase is brief in cosmic terms, while the white dwarf stage represents a quiet, enduring presence that can last longer than many galaxies exist. Finally, the transition from red giant to white dwarf emphasizes the cyclical nature of the cosmos. R Doradus will have contributed its outer layers to the interstellar medium, enriching future generations of stars and planets, and its white dwarf core will persist as a stable relic of its past. In this way, the star's life and death are not just isolated events, they are part of a cosmic chain of creation and recycling, linking the past, present, and future of the galaxy. In summary, the white dwarf core of R Doradus represents the star's final evolutionary stage, a dense, slowly cooling remnant that preserves the star's mass while the ejected outer layers contribute to the birth of new stars and planetary systems. From a giant pulsating red star to a faint but enduring white dwarf, R Doradus exemplifies the full life cycle of a medium-mass star and its vital role in the ongoing story of the universe. The story of R Doradus does not end with its death. In fact, one of the most remarkable aspects of stars like R Doradus is their role in cosmic recycling, the process by which matter is continually reused to form new generations of stars, planets, and even the raw ingredients for life. When R Doradus reaches the end of its red giant phase and begins to shed its outer layers, it will release vast amounts of gas and dust into the surrounding interstellar medium. This material is rich in elements such as carbon, oxygen, nitrogen, and heavier molecules that the star has synthesized during its lifetime through nuclear fusion. This ejected matter forms a circumstellar envelope around the star, eventually expanding into a planetary nebula. While this shell of gas and dust may look like a delicate, ephemeral structure to an astronomer's telescope, it represents the star's contribution to the galactic ecosystem. The elements contained within it are no longer bound to a single star. They become part of the galaxy itself, mixing with interstellar clouds and seeding future generations of stars and planets. In essence, R Doradus transforms from a luminous body into a cosmic gardener, fertilizing space with the materials necessary for creation. This process of recycling is fundamental to the evolution of galaxies. The early universe was composed almost entirely of hydrogen and helium. All heavier elements, collectively called metals in astronomy, were forged inside stars and dispersed into space when stars like R Doradus ended their lives. When a red giant sheds its enriched layers, it contributes not just to the chemical diversity of the galaxy but also to the formation of planetary systems capable of supporting complex chemistry and potentially life. Every carbon atom in our bodies, every oxygen molecule we breathe, was once part of a star like a Doradus. In that sense, the star's death is not a finality but a renewal, a transformation of matter that links past, present, and future. The materials ejected from a Doradus are also critical for the next generation of stars. When interstellar clouds enriched with heavy elements collapse under gravity to form new stars, the composition of these newborn stars is directly influenced by prior generations of red giants and supergiants. A cloud seeded by a Doradus might form a star system with planets that contain water, carbon-based molecules, and minerals, essential components for creating habitable worlds. In other words, the star is literally contributing to the building blocks of planets, moons, and potentially life itself. Observationally, astronomers can study this process in action. The infrared glow of a Doradus, along with spectral lines from molecules in its extended atmosphere, allows scientists to measure the mass loss rate and the types of elements being expelled. Over thousands of years, these materials mix with the interstellar medium, spreading out into the galaxy and becoming part of the vast cycle of star formation and destruction that shapes the Milky Way. The phenomenon reminds us that stars are not isolated objects. They are interconnected actors in a vast, ongoing drama of cosmic creation. This cycle of birth, evolution, and recycling underscores a profound truth about the universe. While individual stars live and die, the elements they produce are eternal. Our Doradus will eventually become a faint white dwarf, but its legacy will persist in the galaxy for millions of years, embedded in the molecular clouds that give rise to new stars. Even after the star's light fades from view, its atoms may find themselves in a planet orbiting a newborn star, in the atmosphere of a future world, or perhaps even in the building blocks of life somewhere else in the galaxy. In this sense, our Doradus is both a giant and a giver. Its vast size and extended atmosphere make it a spectacular object to study, but its ultimate contribution, the elements it returns to the galaxy, is what makes it truly significant in a cosmic context. The red giant is not simply fading into obscurity. It is seeding the universe with the materials necessary for the next generation of celestial objects. Every photon, every molecule, every dust grain expelled during its late life is part of a grand, ongoing cycle that links stars, planets, and living organisms in ways that span billions of years. Cosmic recycling also emphasizes the interconnectedness of the universe. The death of a single star is not an isolated event. It reverberates across space, influencing regions far beyond its immediate neighborhood. When a Doradus sheds its layers, those materials drift outward, mixing with other stellar remnants, interstellar gas, and dust from countless other stars. This intricate mixing process creates the chemical diversity necessary for complex star systems and planetary structures. Essentially, the life of a Doradus becomes part of a galactic tapestry, woven into the ongoing story of the Milky Way. In summary, the cosmic recycling initiated by our Doradus is a crucial part of its legacy. By ejecting enriched gas and dust into space, the star contributes to the formation of new stars, planets, and potentially even life. It transforms from a luminous red giant into a quiet white dwarf, but its materials continue to influence the galaxy for millions or even billions of years. Through this process, a Doradus exemplifies the idea that in the universe, endings are never truly final. They are the seeds of new beginnings. To most observers looking up at the southern night sky, our Doradus appears deceptively simple. Despite being one of the largest stars in terms of physical size, it does not dominate the sky with brilliance the way a star like Betelgeuse or Sirius does. To the naked eye, our Doradus is a faint, reddish point of light, barely distinguishable without truly dark skies. Its apparent magnitude ranges roughly between 5 and 6, which means that under urban conditions with light pollution, it may be completely invisible. Only in areas free from artificial light, or when the night sky is exceptionally clear, can a human observer hope to spot this red giant with unaided eyes. This faintness creates a striking contrast between appearance and reality. While our Doradus physically dwarfs our Sun, over 370 times larger in diameter, it does not radiate enough visible light to appear impressive in the night sky. The reason lies in a combination of temperature, luminosity, and distance. Our Doradus has a cooler surface temperature than the Sun, around 2,740 degrees Celsius, which means much of its energy is emitted in the infrared rather than visible light. Its proximity of roughly 200 to 230 light-years brings it close enough to be seen without a telescope, but it still lacks the brightness to be prominent compared to other nearby stars. As a result, to a casual stargazer, R Doradus is unassuming, a quiet member of the constellation Dorado rather than a spectacular feature. Its reddish hue may be perceptible under dark skies, hinting at its nature as a red giant, but the star does not fill the sky in any visually dramatic sense. This is why R Doradus is often overlooked in popular astronomy guides. It doesn't have the fiery intensity of Betelgeuse or the brilliance of Rigel. This subtlety, however, is what makes R Doradus particularly fascinating for astronomers. Its faintness in visible light belies the immense scale and complexity of the star. Using telescopes, interferometers, and infrared instruments, scientists can detect its enormous angular size, observe pulsations, map its extended atmosphere, and study the processes by which it sheds mass into space. In other words, while it may look like a small, faint dot to the human eye, it is actually a cosmic laboratory revealing the secrets of red giant evolution. The fact that R Doradus appears faint also underscores a broader truth about the night sky. Visual brightness does not necessarily correlate with size. Many stars that dominate our view, like Sirius, are relatively close and very luminous, but small in diameter compared to red giants or supergiants. Conversely, giants like R Doradus may be enormous yet inconspicuous because their light is emitted in wavelengths our eyes are not sensitive to, or because their energy is spread over a cooler surface. For those who do manage to spot it with the naked eye, the experience is subtle but rewarding. You're seeing a star so enormous that if it were placed where the Sun is, it would almost engulf the Earth's orbit. Yet all that scale is condensed into a faint speck. It's a humbling reminder that the universe does not reveal its size or power at first glance. Some of the most extraordinary phenomena are almost invisible without careful observation. In essence, naked eye observers see only the tip of the iceberg. R Doradus looks modest, but its true nature, an enormous, pulsating red giant with a thick atmosphere, strong infrared emission, and a dynamic environment, is hidden from casual sight. It serves as a reminder that the night sky holds wonders that are often invisible without the aid of science and technology, and that even faint stars can have outsized importance in our understanding of stellar evolution. What makes R Doradus particularly special to astronomers is not its naked eye brilliance, but its proximity and the opportunities this provides for detailed observation. At roughly 200 to 230 light-years away, R Doradus is one of the closest red giants to Earth, and this closeness transforms it from a faint, inconspicuous star into an extraordinary laboratory for studying the late stages of stellar evolution. Its nearness allows astronomers to resolve features and measure properties that would be impossible for more distant giants, even those far more luminous. One of the key advantages of proximity is the ability to measure its angular diameter. Because R Doradus is relatively near, it subtends a larger apparent size in the sky than many of the physically larger but more distant red supergiants. Techniques like interferometry can detect and resolve its disk, providing detailed measurements of its size, shape, and surface structure. For most red giants, even enormous ones, such measurements are extremely challenging because their apparent size is too tiny. R Doradus, being nearby, is just large enough on the sky to make these studies feasible. Its closeness also allows astronomers to observe the extended, fuzzy atmosphere with far greater precision. R Doradus's atmosphere is highly dynamic, filled with convection currents, pulsations, and molecular clouds. These features are more readily detectable in nearby stars, because the light we receive is less diluted and the angular resolution needed to distinguish structures is more attainable. In essence, R Doradus gives astronomers a direct window into the physical processes occurring in a red giant's outer layers, something that is almost impossible for stars located thousands of light-years away. Another significant advantage is studying its pulsation behavior. R Doradus is a semi-regular variable star, meaning its brightness changes over time due to expansions and contractions in its outer layers. Because it is close, these pulsations produce detectable changes not just in brightness but also in apparent size, infrared emission, and spectral features. Astronomers can monitor these cycles over years or decades to understand the mechanics driving pulsations, convection, and mass loss in red giants. These observations are critical for refining theoretical models of stellar evolution. Moreover, R Doradus's proximity allows for multi-wavelength observations with unprecedented detail. Instruments ranging from optical telescopes to infrared interferometers can study different layers of the star simultaneously. Infrared observations reveal the cool, dusty outer atmosphere, while visible and near-infrared measurements probe deeper layers. By combining data across the electromagnetic spectrum, astronomers can construct a comprehensive, three-dimensional understanding of the star, something that is practically impossible for more distant red giants. Its relative closeness also makes R Doradus an ideal target for testing stellar atmosphere models. The physics of red giants is complicated. Temperature gradients, molecular chemistry, and pulsation-driven mass loss all interact in ways that challenge theoretical predictions. Observations of nearby stars like R Doradus provide the data needed to validate these models. In this sense, it's not just a star in the sky. It's a benchmark for understanding a whole class of stars. Finally, R Doradus serves as a stepping stone to studying the life cycle of stars like our Sun. While our Sun will never become a red supergiant as large as R Doradus, it will eventually evolve into a red giant and follow a somewhat similar path, shedding its outer layers and leaving behind a white dwarf. By studying R Doradus, astronomers can observe the processes of pulsation, mass loss, and chemical enrichment in a nearby star, gaining insights into the fate of medium-mass stars and the future of our own solar system. In short, the specialness of R Doradus to astronomers lies in its combination of size, evolutionary stage, and closeness. Its proximity makes it one of the few red giants where detailed, multidimensional observations are possible. While it may appear faint to the naked eye, for scientists it is a cosmic laboratory, offering a unique opportunity to study the physics, chemistry, and dynamics of stars approaching the end of their lives. It allows us to see phenomena that would be invisible in more distant giants and to refine our understanding of how stars evolve, pulsate, and recycle matter into the galaxy. The scientific importance of R Doradus extends far beyond its status as a nearby red giant or its size in the night sky. For astronomers, it serves as a crucial piece in the puzzle of stellar evolution, particularly for stars in the intermediate mass range that are not massive enough to end as supernovae but are far larger than our Sun. Studying R Doradus helps us understand not only how stars live and change over time, but also how they die and return their material to the galaxy. R Doradus is a prime example of a star on the asymptotic giant branch, AGB, a late evolutionary stage characterized by hydrogen and helium shell burning around an inert carbon-oxygen core. Stars in this phase experience enormous expansion, pulsations, and mass loss, all of which play a key role in their eventual transformation into white dwarfs surrounded by planetary nebulae. By observing R Doradus, scientists can see these processes in action, rather than relying solely on theoretical models. The star's proximity makes it possible to measure changes in its size, brightness, and atmospheric composition with precision, providing data that refine our understanding of AGB stars. One of the critical scientific questions R Doradus helps address is how stars lose mass. The mass loss process determines a star's final fate, influences the composition of the planetary nebula it will form, and contributes to the enrichment of the interstellar medium. Through observations of R Doradus's pulsations and extended atmosphere, astronomers can study the mechanisms driving stellar winds, the role of dust formation, and the dynamics of molecular layers. This information is essential for understanding how stars shed material into space and how these materials contribute to the next generation of stars and planets. R Doradus also provides insight into stellar pulsation mechanisms. Its semi-regular variability is caused by the expansion and contraction of its outer layers, which can trigger shockwaves and alter the star's brightness. By monitoring these pulsations over time, astronomers can test and refine models of stellar interiors, learning how convection, radiation pressure, and shell burning interact to produce observable changes. Such studies have broader applications, helping scientists predict the behaviors of other red giants and understand the late stages of evolution for stars of similar mass. Another important aspect is chemical enrichment. The elements produced inside R Doradus during nuclear fusion, including carbon, oxygen, and heavier molecules, are eventually ejected into space. Observing these processes in real time allows astronomers to quantify how stars contribute to the chemical evolution of the galaxy. This is a key factor in understanding the origin of the elements that make up planets, atmospheres, and even life itself. Without stars like R Doradus recycling their material, the universe would be a far less chemically diverse place. The star's relatively close distance also makes it an ideal benchmark for testing theoretical models. While more distant giants or supergiants may be brighter or physically larger, their vast distances make high-resolution observations extremely difficult. R Doradus allows astronomers to compare predictions of stellar size, temperature, pulsation amplitude, and mass loss rates with actual observations. This feedback loop between theory and observation is fundamental to advancing our understanding of stellar physics and improving the accuracy of models used across astrophysics. Furthermore, R Doradus helps astronomers understand the end stages of stars similar to the Sun. Although our Sun will never become a red giant as massive as a Doradus, it will eventually undergo similar processes, expanding, losing mass, and forming a planetary nebula before leaving behind a white dwarf. Observing a Doradus provides a glimpse into the distant future of our own solar system, showing the complex interactions between pulsations, mass loss, and atmospheric chemistry that shape a star's final years. In a broader sense, R Doradus exemplifies the interconnectedness of stellar life cycles. Its evolution informs our understanding of how stars influence galaxies, how elements are distributed, and how stellar populations evolve over time. Every detail we learn about a Doradus, from its pulsations to its mass loss patterns, feeds into a greater understanding of the universe, helping us interpret the life cycles of stars far beyond our immediate neighborhood. In conclusion, the scientific importance of R Doradus is immense. Its size, proximity, and late evolutionary stage make it a laboratory for studying how stars expand, pulsate, shed mass, and enrich the galaxy. Observations of this red giant illuminate fundamental processes in stellar evolution, from the mechanics of pulsation to the recycling of elements into new stars and planets. By studying R Doradus, astronomers gain a deeper understanding of how stars evolve and die, providing insight not only into the universe's past but also into its ongoing processes of creation and renewal. To truly grasp the immense scale of R Doradus, one of the most striking ways is through a simple, fun, imaginative comparison. What if a Doradus were placed where our Sun is? The result is a jaw-dropping visualization of stellar proportions. With an estimated diameter roughly 370 times that of the Sun, this red giant would dwarf all the planets in the inner solar system. Its surface would extend past Mercury's orbit, engulf Venus entirely, and come close to reaching Earth's orbit. Let's break this down in numbers to better understand the magnitude. The Sun's diameter is approximately 1.39 million kilometers, which is already enormous compared to Earth's 12,742 kilometer diameter. Multiply that by 370, and you get a star roughly 514 million kilometers across. For reference, Mercury orbits at about 58 million kilometers, Venus at roughly 108 million kilometers, and Earth at 150 million kilometers from the Sun. A Doradus, if positioned at the center of our solar system, would literally swallow Mercury and Venus whole and almost brush Earth. The inner planets, in this scenario, would cease to exist as distinct bodies, being fully immersed within the star's scorching atmosphere. This comparison is not only astonishing in scale, but it also helps illustrate the sheer size differences among stars. While the Sun appears large to us in everyday terms, R Doradus is orders of magnitude bigger. Even Jupiter, the largest planet in the solar system, would be minuscule next to this red giant. Its diameter would fit hundreds of times across the star's immense surface. Visualizing a Doradus in this context transforms abstract numbers into something tangible, a star so vast that it swallows planetary orbits whole. This kind of thought experiment also emphasizes the limits of human intuition. Even though we can see R Doradus as just a faint dot in the night sky, its actual size is almost unimaginable. The faint reddish light that reaches our eyes masks a colossal, turbulent sphere of plasma, gas, and dust, hundreds of millions of kilometers across. Comparing it to familiar distances in our solar system, planetary orbits, is a rare opportunity to relate the cosmic scale to something tangible. Such a comparison also illustrates why astronomers are so fascinated by stars like a Doradus. Studying a star that could engulf the inner planets in a hypothetical scenario allows us to better understand the extremes of stellar evolution. It helps us grasp the upper limits of red giant expansion and the types of environments that form around dying stars. These insights inform models not only of R Doradus itself but of all medium-mass stars, including the eventual fate of our Sun. In addition to scale, this example sparks wonder and curiosity. Thinking about a star so enormous that it could nearly reach Earth's orbit reminds us of our small place in the universe and the staggering sizes that stars can attain. It's one thing to hear that a star is hundreds of times larger than the Sun, but quite another to imagine the Sun replaced by such a giant, with the inner planets completely engulfed. It transforms an abstract concept into an almost cinematic visualization of cosmic immensity. In essence, the fun comparison demonstrates two things simultaneously. First, the astounding physical size of a Doradus, and second, the contrast between appearance and reality. To the naked eye, it's a faint red speck in the constellation Dorado, yet if placed in our solar system, it would dominate the inner planets, a colossal sphere of gas and energy. This juxtaposition highlights how distance and wavelength perception can hide true scale in astronomy, making a Doradus appear modest in brightness while being astronomically gigantic in size. Ultimately, this comparison is not just a curiosity, it's a tool for perspective. By imagining a Doradus in our solar system, we can better appreciate both the magnitudes involved in stellar physics and the incredible processes at work in red giants. It's a playful yet profound way to connect the abstract numbers of stellar diameters and orbital distances to a more intuitive and human-scaled understanding of one of the universe's most enormous stars. To truly appreciate a Doradus, it helps to engage your imagination and picture its scale in a way that stretches your mind. Numbers and measurements can give us a sense of size, but they often fail to capture the staggering reality. Our Doradus is not just bigger than the Sun. It's a cosmic behemoth so enormous that it could engulf the orbits of entire planets in our solar system. Visualizing it in this way can transform a faint red in the night sky into a tangible, awe-inspiring entity. Start by picturing the Sun at the center of the solar system, the anchor of our planetary neighborhood. Now, imagine inflating that Sun 370 times in diameter, turning it from a familiar, brilliant sphere into a gargantuan red giant. Mercury, orbiting at 58 million kilometers, would vanish inside its atmosphere. Venus, at 108 million kilometers, would also be fully swallowed. Even Earth, orbiting at 150 million kilometers, would be nearly touched by its blazing outer layers. This is a star so massive that distances we normally associate with planetary motion are mere fractions of its surface radius. To go even further, think about the scale of movement within the star itself. Our Doradus's atmosphere is turbulent, filled with convection cells that rise and fall like immense storms, each spanning hundreds of millions of kilometers. These cells would dwarf the Earth multiple times over, creating hot plumes and cooler regions that shift over months. Its pulsations expand and contract the outer layers, slightly altering its radius, sending shockwaves through the atmosphere and reshaping the star continuously. It's a living, dynamic system on a scale almost impossible to fully visualize. Now consider the orbit of Mars at 228 million kilometers. While our Doradus wouldn't reach Mars if placed at the Sun's position, its sheer magnitude would come uncomfortably close to the inner planetary zone. If we try to extend our imagination beyond numbers, you can picture Earth not as a planet orbiting a sun, but as a speck trapped within the outer reaches of a massive, luminous red ocean of plasma. It's a striking demonstration of how enormous stars can become in the red giant phase, small points in our sky, yet titanic in reality. The visualization gets even more dramatic when you consider the mass loss process. As a Doradus pulsates, it ejects material into space, forming an extended envelope of gas and dust. This material gradually drifts outward, potentially stretching beyond the scale of inner planetary orbits, creating a dynamic and ever-changing environment. Now, imagine standing somewhere within the vicinity of these outer layers. You wouldn't see a clean, spherical surface, but a fuzzy, semi-transparent ocean of gas, moving and glowing in infrared light. One of the most remarkable aspects of this scale is the contrast between size and perception. From Earth, even with binoculars, our Doradus appears as a faint, reddish point of light. Yet in reality, it is a star that could swallow entire orbits and dwarf entire planets. This teaches a humbling lesson. Appearances can be deceiving in astronomy. The universe is filled with objects whose physical magnitude far surpasses their apparent brightness, and our Doradus is a perfect example. To help cement this visualization, imagine a series of concentric circles representing planetary orbits around a central point, the Sun. Then, overlay a massive red sphere representing our Doradus at the center. The inner circles of Mercury, Venus, and almost Earth disappear inside the star. The outer circles of Mars and Jupiter remain, but the inner solar system is completely engulfed. This simple mental model allows us to conceptualize the enormity in a way that raw numbers alone cannot convey. Finally, consider the emotional and intellectual impact of such a visualization. A star so large that it could envelop planets challenges our understanding of scale and pushes our imagination. It reminds us that the cosmos operates on dimensions far beyond human intuition. While a Doradus may seem small and faint in our sky, its physical presence is awe-inspiring, and contemplating its size can deepen our appreciation of the vastness and diversity of stellar evolution. In short, imagining the scale of a Doradus is about more than just numbers. It's about perspective. It's about envisioning a star so immense it could swallow entire orbits, turbulent and glowing with energy, reshaping its surroundings as it pulsates. Visualizing this helps us connect with the universe on both an intellectual and emotional level, turning a faint red in the sky into one of the most spectacular natural phenomena imaginable. When we step back and summarize the uniqueness of a Doradus, it becomes clear why this red giant is such a captivating object for both astronomers and anyone intrigued by the cosmos. At first glance, it may seem unremarkable, a faint red speck in the southern constellation of Dorado, easily overlooked by naked-eye observers. But this modest appearance masks a star of immense physical scale and scientific significance, making it truly extraordinary. Physically, our Doradus is enormous. With a diameter estimated at around 370 times that of our Sun, it could engulf the orbits of Mercury and Venus, and nearly reach Earth if placed at the center of our solar system. Its extended, turbulent atmosphere, pulsating behavior, and semi-regular variability add layers of dynamism, showing us a star in constant motion rather than a static sphere. Despite its size, its visible brightness is modest due to its cooler surface temperature and emission mostly in the infrared, creating the striking contrast between apparent faintness and true magnitude. Its proximity makes a Doradus even more exceptional. At just over 200 light-years away, it is one of the closest red giants to Earth, and this relative closeness allows astronomers to study its structure, pulsations, and mass loss processes in remarkable detail. Techniques like interferometry and infrared imaging reveal features in its atmosphere and envelope that would be completely unresolvable in more distant giants. In many ways, our Doradus serves as a cosmic laboratory, providing data that helps refine models of red giant evolution, mass loss, and stellar chemistry. Scientifically, our Doradus is invaluable. Its study informs us about the final stages of stellar evolution for medium-mass stars, helping us understand how stars expand, pulsate, shed material, and ultimately transition into white dwarfs. Its material will enrich the interstellar medium with elements such as carbon, oxygen, and nitrogen, contributing to the cosmic recycling that seeds the next generation of stars and planets. In this way, the star's life and death are deeply intertwined with the ongoing creation of the galaxy itself. Another aspect of its uniqueness lies in the contrast between perception and reality. To the human eye, it is faint and understated, barely noticeable against the backdrop of the night sky. Yet scientifically, it is massive, complex, and dynamic, offering insights into stellar physics that far surpass what is immediately visible. This duality makes a Doradus an excellent reminder of how much the universe hides beneath appearances. Spectacular phenomena often require careful observation and technological tools to reveal their true nature. Finally, our Doradus embodies scale, proximity, and scientific relevance all at once. Its enormous physical size, relatively nearby location, faint visual brightness, and observable pulsations combine to make it one of the most studied red giants in the sky. It is a star that simultaneously humbles and enlightens, showing us the incredible scales involved in stellar evolution while providing practical data to deepen our understanding of the cosmos. In essence, our Doradus is huge, nearby, faint to the eye, but massive to science. It reminds us that the universe is filled with objects whose significance cannot be judged solely by appearance, and that the study of even seemingly modest stars can yield profound insights into the workings of the cosmos. Its pulsations, size, mass loss, and eventual transformation into a white dwarf all make it an indispensable subject for astronomers seeking to understand the life cycles of stars and the enrichment of the galaxy. The story of our Doradus is far from complete, and the future of its study is poised for remarkable advances thanks to the latest generation of astronomical instruments. One of the most exciting prospects comes from new telescopes such as the James Webb Space Telescope, JWST, which promise to reveal details about a Doradus that were previously impossible to observe. While past ground-based telescopes and interferometers have given us invaluable insights into its size, pulsations, and atmosphere, JWST's advanced capabilities, particularly in the infrared spectrum, open entirely new windows into this nearby red giant. R Doradus emits most of its energy in infrared light due to its relatively cool surface temperature of around 2,700 to 2,800 degrees Celsius. Ground-based telescopes can only detect portions of this emission because the Earth's atmosphere absorbs and distorts infrared light. JWST, positioned above the atmosphere, can observe the full range of infrared wavelengths with unparalleled sensitivity and resolution. This will allow astronomers to study fine details of the star's outer layers, dust formation, and molecular composition in ways never before possible. For instance, JWST can detect and map molecules like water vapor, carbon monoxide, and complex hydrocarbons in R Doradus's extended atmosphere, revealing the chemical processes that occur as it loses mass. Another area where JWST can make a major impact is in the study of stellar pulsations and variability. R Doradus is a semi-regular variable star, meaning its brightness changes over time as its outer layers expand and contract. JWST can monitor these changes in the infrared with high precision, allowing astronomers to track pulsation patterns, amplitude variations, and temperature fluctuations across the star's surface. This level of detail will help refine models of red giant pulsations and improve our understanding of the physical mechanisms driving mass loss, which is critical for predicting how stars like R Doradus evolve and eventually form planetary nebulae. JWST's imaging and spectroscopic capabilities will also shed light on the structure and dynamics of the star's extended atmosphere. The outer layers of R Doradus are not uniform, they are turbulent, with convection currents, shock waves, and localized density variations. By observing these features at multiple infrared wavelengths, astronomers can create three-dimensional maps of the star's atmosphere, tracking how material moves outward and how dust and gas are ejected into space. These observations will help answer long-standing questions about the mass loss processes in red giants, which are a key factor in the chemical enrichment of the galaxy. In addition to JWST, other next-generation telescopes and instruments will complement these observations. Ground-based interferometers with larger baselines, such as the upgraded Very Large Telescope Interferometer, VLTI, will continue to refine measurements of R Doradus's diameter and surface structure. Radio and submillimeter observatories, like ALMA, Atacama Large Millimeter Submillimeter Array, can trace molecular emissions and dust formation in the circumstellar envelope. By combining these datasets, astronomers can achieve a multi-wavelength, multidimensional understanding of the star's complex behavior. Future observations will also allow scientists to study R Doradus in the context of other red giants. By comparing high-resolution data from JWST and other instruments, researchers can determine which features, such as pulsation amplitude, atmospheric composition, or mass loss rate, are typical of red giants and which are unique to R Doradus. This comparative approach will help astronomers build more accurate evolutionary models for medium-mass stars and refine predictions about the future of similar stars, including our Sun. Beyond pure scientific inquiry, future observations of R Doradus carry the potential to inspire public fascination and wonder. High-resolution infrared images of a nearby red giant, showing its massive, dynamic atmosphere and pulsations in exquisite detail, can make the abstract concepts of stellar evolution tangible. Viewers will be able to see a star that, while faint in visible light, is a colossal, ever-changing world of plasma, turbulence, and infrared glow, bringing the immense scales of the cosmos into sharper focus for both scientists and the general public. In short, the future of observing R Doradus is incredibly promising. The James Webb Space Telescope, along with other advanced instruments, will allow astronomers to probe its size, atmosphere, pulsations, and chemical composition with unprecedented clarity. These observations will deepen our understanding of red giant stars, their mass loss processes, and their role in cosmic recycling. With new data from these cutting-edge telescopes, R Doradus will continue to serve as a cornerstone for studying the life and death of stars, providing insights that will shape our knowledge of the universe for decades to come. As we draw this journey through the story of R Doradus to a close, it's worth pausing to reflect on what makes stars like this so profoundly awe-inspiring. From the casual stargazer's perspective, R Doradus is little more than a faint reddish in the southern sky, quietly hanging in the constellation Dorado. Yet behind that modest appearance lies a colossal, pulsating, dynamic sphere hundreds of times the diameter of our Sun, with an atmosphere extending far into space, sending enriched material into the galaxy, and offering astronomers a living laboratory to study the life cycle of stars. The night sky is full of such contrasts, objects that seem ordinary at first glance but reveal extraordinary properties upon closer examination. R Doradus embodies this paradox perfectly. It is massive in physical scale, yet faint in visible brightness, close enough to study in detail, yet far enough away that the light reaching Earth left over 2 centuries ago. Its pulsations, mass loss, and extended atmosphere tell a story of stellar life and death that spans millions of years. Yet we can witness key moments of this story in real time through modern astronomical techniques. Beyond its scientific significance, R Doradus also serves as a reminder of the sheer scale and variety of the cosmos. Thinking about a star so large that it could nearly engulf Earth's orbit forces us to expand our mental horizons, to consider scales of size, energy, and time that are far beyond everyday human experience. It challenges our intuition, inspires curiosity, and demonstrates that the universe is filled with phenomena that both humble and excite us. Stars like R Doradus also remind us of the interconnectedness of cosmic processes. From the elements forged in its core to the planetary nebula it will eventually create, R Doradus contributes to the ongoing cycle of creation and recycling in the galaxy. Its death will feed the formation of new stars and planets, influencing the chemical makeup of future generations of celestial objects. In this way, even a faint star in the sky is deeply tied to the broader story of the universe, a story in which all matter, energy, and life are linked through countless generations of stellar evolution. Finally, R Doradus inspires us to look up with wonder. Every time we gaze at the night sky, we are witnessing a tapestry of cosmic history, a vast collection of objects whose lives span billions of years and whose scales challenge our imagination. Stars like R Doradus demonstrate that the universe is not static. It is dynamic, evolving, and full of surprises. The faint points of light we see are not just distant suns. They are gigantic, complex, and active worlds, each with a story to tell about creation, transformation, and the passage of time. In closing, R Doradus is more than a red giant in a southern constellation. It is a symbol of the universe's grandeur, a reminder that the cosmos contains objects so massive, so powerful, and so intricate that they stretch the limits of our imagination. Its faint glow challenges us to look closer, think bigger, and appreciate the hidden wonders of the night sky. Whether for astronomers unraveling the mechanics of stellar evolution or for anyone gazing upward in awe, R Doradus stands as a testament to the astonishing scale, beauty, and complexity of the universe. So the next time you look up at the night sky, remember, even the faintest stars can hide colossal secrets, and some, like R Doradus, are massive enough to dwarf entire worlds, enrich the galaxy, and teach us about the grand cycles of creation and renewal that define the cosmos. In every twinkle of distant light lies a story waiting to be explored, and R Doradus is one of the most spectacular chapters in that cosmic narrative. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.